slow. You know what happened? It
It's become harder and harder.
I should stand at the front and
Uh,
see.
Ah, nice to meet you.
Nice meeting you. Yes. Thank you for taking the time coming all the
Oh,
way
it's
here.
nice. It's a pleasure. It's a bit concentrate, but it's okay.
Right, great. So actually I have a personal interest in this topic. I'm not in this area at all.
Yes.
I'm a control systems guy. But I'm interested in this variable refrigeration system, vapor absorption, not variable, vapor absorption. So I'm trying to think about, okay, how can I, whether it will be economic for Assam or not, that's a big question for this particular climate. But solar collectors will play a big role.
You
Because
have
Yes.
covered almost all the topics of solar collector. Cooling and heating.
but I
is
thought
today-
heating and cooling is
yeah,
today,
cooling
right?
today is,
So
Yes, today, yes, it is that, and for sure, for the control, there is an issue regarding coupling solar with thermodynamic machine because they don't like to be unstable,
I see.
whereas solar could be unpredictable
Right.
or
He's
variable.
professor in USA in one of the universities.
Okay,
And,
Came back
from
3 years ago.
nice to meet you.
Okay, cool. I'm looking forward to
We have a
lecture.
joint student.
Ah, okay,
He's working on
Vapor absorption.
vapor absorption.
okay, nice. I'm not sure there is too much people so connected. Hello,
Yeah.
only 4.
Maybe we can start.
We start?
So I. So I welcome you to the first session on day 4, and then there will be tutorials. No, so today mostly the solar thermal cooling and heating content will be discussed, and I request all of you to be attentive because this is very important topic in both in our countries as well as in Western countries. So now, Professor, you can
Okay.
start.
Yes, so we will continue on the tutorial of yesterday, and I had some explanation regarding especially this value. So if you remind me what we have seen in my day and one lecture, page 112, there was a small design of autonomous installation, and for the peak power of the global PV central, we said that it is equal to the energy needs divided by the performance ratio, the efficiency of the battery and of conversion to the battery, and the mean solar radiation per month. Okay. So if we look, we are doing the reverse. We know the energy, we know the power peak. We a priori select a panel, okay? And this, we don't have to forget that it is for standards. So when we say that the peak power of PV panels is at 140, as we select, it is 140 watt per 1000 watt per square meter in standard condition. So it is a reason why when we multiply this power by the mean radiation we selected 5 kilowatt hour per square meter per day. It is simplified with that, okay? So we will obtain some watt or some kilowatt, depending of what we said as a peak power. I am clear or no? Here, the energy produced by a PV panel, we said it is the peak power, and it is in watt. Multiply by the EJP per day, okay? But this peak power is okay, in standard condition. So when we multiply this by this, there is a simplification of kilowatt. Okay. That is because there was a question, why is it we have forgotten. I was too tired yesterday evening to identify the thing. Is it clear like this? Okay. So it is the estimation of what is produced per day by one panel is this. Okay. The other thing where you are right, they made a mistake. I made the mistake here. So you're right, it is 70. So 70 panels. So it will change my data application, but I'm trusting you to give me the good value, okay? So après, we have to integrate 70 solar PV panels of Siemens branch 140 with 12 volt at the born of the PV panels. And now the next question was how much we put some PV panels in a string. So this is a string, we call that a string. How much in series and how much string in parallel. We have seen that it is advised that for the range of the power of our PV central, what is usually adopted, it is, we are in this range, it is 48 volts in open circuit for the central. So the first is quite simple. How many here? How many solar PV collector in series? Four. Okay, because we said that we select this, so which has a peak power of 140 and an open circuit tension voltage of 12. So for sure we have to put 4 PV panels. Okay? Don't hesitate, because when you put in series, you add the voltage. Okay? Then I told you that a PV central has to be balanced. Okay? So we can't imagine to put 4 here, 4, 4, and 3. Okay? 4 will be a constant number for the string. So now if you said that I have 4 PV panels per string, if you divided 70 by 4, it should give you an idea of the number of parallel strings. So can you compute it, because I didn't do that?
17.5.
Sorry?
17.5. So you can take 18.
15?
18.
1 8. So if you do the calcul, you find that? That's it? Okay. So 70 divided by 4 is equal to 17.5, and it's right. You will select 18. Never below, but okay, up. So 18 string. So it is modifying a bit the global solar power peak of the centrals. Okay, can you give me the global power? So finally, it is how many PV modules? Seventy-two multiplied by 104. So you have 10. The power of your PV central is 10.08 kilowatt peak. Okay? Everybody is okay with that? Okay, so I'm good on this for sure. I'm bad on this. It is 18. Okay. You have also a rough idea of the inclination of the panels depending of the latitude. Okay, the inclination, the best inclination is obviously depending of the latitude. The more the latitude is high, the more the panels are going to the vertical. Okay, the more the latitude is low, the more the panels are going near the horizontal. Okay. A remark that I have made yesterday, but it is very important. This kind of evaluation of inclination is made for a maximum generation of energy during the year. Okay? It seems to be obvious, but we can admit that in some cases we would like to have more production of energy during winter, where we need a lot of energy, than within summer when we produce a lot of energy, but sometimes we don't need it. Okay. So this remark is that it is important for maximum of production of energy because it is an autonomous central. If it was on the grid connected, it could have been different. Okay. So thus, in our case, we will choose an inclination of 15 degrees. So it's not really inclined, okay? So this I will give you on the package also. So you just have to correct the right data, but this will be integrated. Okay, now sizing of the battery. So, I didn't remember if I told you to take a discharge. So we have several batteries, okay, that are available in place. So lead battery are the more common. There is also gel battery. So we have to put also 48 volts, okay, in a rack of the battery. So to connect the battery in order also to be consistent with the PV central and to have 48 volts. As I remind you, if I have two batteries in series, I take this one, 6 volt, 300 ampere hour. It's equivalent to a battery. So what are the characteristics of the equivalent battery? Yes, you had the voltage, so 12 volt and 300 ampere hour. Whereas is in parallel, it will stay 6 volt and 600. Okay. So we will choose this one. Okay, because the other have too small voltage. We will have to put a lot, and the other could be less rare and not so mature. Okay, you can choose another one if you want, but we will select that. So they can be put together in series or parallel in order to at the end obtain 48 volts. Okay. Of course, the number of the battery is depending of the autonomy we want. Okay, at that time we didn't discuss about the autonomy, which is a key element, of course, for the battery. So what I suggest to you when I was introducing that is that you have to investigate local climate, okay, to see if it's a country where it is sunny every day, the rain is very rare, or if there's some period where you have no sun for several days and so on. First, investigate the local climate. Second, discuss with the customer. Okay, this is a school, donc a priori it's not operating the weekend, and so only 5 days, and maybe not in the period where there is bad weather or at the rivers, where there is a very sunny river. Okay, so it has to be to know, to investigate local data. Okay, so today we don't know, we have not the possibility, but usually when you have a battery rack, you choose around 2 or 3 days of autonomy. Okay, but it could be more precise, discussing with the customers what is the use of the building, the period of the use of the building, and also local climate. If there's some specific climate, there is fog, for example, for 2 months in the year, it's delicate. Okay, so we'll choose 3 days. Okay. Assumption. Okay. But in reality, you go deeply locally to understand what are the real needs. Okay, don't forget that. It has to be consistent with the use. Okay, so I decided that my battery have to be able to store 3 days of energy need. So around 145.86 kilowatt hour. So it is the same like for the PV panel. You have seen, you had them, you connect them in series, you had the voltage. So here it's easy to see that you will have 4 times this. That means 8 battery per string. And then after you complete to have your global autonomy. Okay, so we will connect 8 battery per string. To obtain a voltage of 48 volts. And then we identify the number of parallel string in order to reach our autonomy. Okay? So I leave you to think about that a bit. You see, the price of a battery is quite high. When you have a PV installation and you had some battery, it's increasing a lot because PV panels now are very inexpensive. All the other components are non-expensive. So it is the reason why that grid-connected PV installation and off-grid connected has nothing to compare in terms of price. Yes, the main price of this kind of installation in the battery.
While selecting the voltage, do we need to see the specification of the inverter?
Yes, the inverter has to be consistent with the inverter has to be consistent of the global power of the central, because the inverter helps to find the maximum power. Is tracking the maximum power, so it has to be consistent with the global power of the PV central. Also, the voltage has to be taken in consideration, but it is the maximum power that will help to design the inverter. Okay, so I said that number of battery is dependent of this autonomy. we select a depth of discharge of 80%. 80%, it is the maximum in your assumption. Huh? Remember, the more you are going deep in the extraction of energy in the battery, the less the battery lifetime will be. Okay, the shorter, but it is linked to the number of cycles and the depth of the discharge. So to be very comfortable and to have no problem in terms of maintenance, it's good to take 50%, but that means that you are doubling. If you just use half of the capacity, you are doubling the number of battery. So it's very expensive at the investment and less for the maintenance. So it depends also of the economic model you have. If you have a lot of money to invest, be comfortable and take a discharge of 50%. If you are just regarding the investment, you take 80% of use of the discharge, okay?
As part of plan, now we have this air cooling. So that's how they have planned it now.
Yeah, but I finished that and then I'm doing that. Yes?
I got a message that people are waiting there for this lecture.
But they don't follow all? They should follow all my lecture, no? No, I will. It will be in the second part. But I want to finish this, it will almost finish. Okay. So, yes, and if you take this value, you have to know that the lifetime will be shorter, so you have to plan to invest during the life of the central. Okay, so we said 8 battery must be connected in series, okay. Like this, the total energy to be stored in the battery is just equal to this. If we consider, so this is when we consider that we are using all 100% of the battery. Huh? And if you consider only that you use 80% of the battery, you measure, okay, this. So thus, we need 127 batteries. And so I will leave you check. If you find there is a problem, you will tell me and we will correct. Okay, but I'm almost sure about this. So the inverter, so I suggest one kind of inverter that is able to deal with 12 volt, 24 or 84 volt, and of course related to the power that we have in our PV central. So this, the name don't give you the data of the inverter, but if you look at this, I will give you there is a power, so the maximum power, which is really consistent with the peak power of the PV central. Okay.
So how that totally will be calculated?
Sorry.
3039 ampere hour. How that?
Yes, it is the total of the storage capacity when we are connecting all the battery. Yes.
Series and parallel also.
Yes. If we use 100%, but we don't use 100%, so we have to measure. We have to add 20% of this. This is equal to this plus 20% of this to measure, okay? Because we are using only 80%. Well, this is to finish on the cost estimation, depending of the price that I give before, okay? So you see, it's quite simple. If you have further question about the installation, you can write me, and okay, it was to have a ROS design regarding PV, regarding the battery rack. In between there is the inverter. Inverter, the main thing is to be consistent with the maximum power of the PV central, so it is the peak power of the PV central. Remind that if the inverter is under design, so is not able to deal with the level of the peak power of your PV central, sometime when it is very sunny, very cool, the PV central could be close to its PV peak power, and the inverter, if it is under design, we will not be able to follow and to identify the peak power, okay? The maximum power, sorry. If it is the case, it is disconnecting the PV central. That means that all what is produced will not be used, okay? It is less sensible if the inverter is oversized. If it is oversized compared to the peak power of the PV central, you will lose some kilowatt hour because of accuracy. Okay, if it is too oversized, it will not be accurate enough to identify the maximum power. Okay, so you can lose. It could maybe be just a bit below, just a bit higher, or so, and below, not higher. So you can lose a bit of energy production, but it will never be disconnected to the application. Okay. But if it is not well sized and below the maximum peak power, you can lose a lot, because if it's disconnecting, it will disconnect until the power will become low enough to be able to track it. Okay. So it's better to oversize, but to be closest as possible. Is it clear how to design? So of course, after you have the tools. This is a ROS design to just give an idea. Then after, when you have this data, you can go on simulation tools that will give you a more specific and precise design. Okay, but at least you will not be far from that. But the tools will allow you in this particular place. Remember, if there is mask, if there is, you will have the real meteo file. So you can say, you can identify on 1 week how much you will produce in winter, on 1 week how much you will produce in summer. So, but it's just to have a good a rough idea. Okay. Okay, so now we can start by what is planned today. So solar heating and cooling lecture. Keep no. Okay. Yes, it is. So yes, PDF. Okay. So now we will go on the solar thermal side and see what we can do with this energy vector. Okay, so to remind you, there is two way, two big family of solar PV that we just deal with, and solar thermal. With solar thermal, it's a low density, so there is different technology, but it's going to low temperature. We can reach very high temperature. We have seen solar furnace, okay, but it depends on the technology. And if you want to reach higher temperature, you have to develop the surface or to concentrate and to concentrate the energy, and you can generate electricity. So to meet heating needs, you have heating and domestic hot water, so we'll see solar thermal. To meet cooling needs, there is direct solar PV coupling with heat pump. There is nothing special in the lecture that we will do. We will see how a solar thermal cooling system can replace a solar PV cooling system. Okay. So we can make some cool through heat, and to meet energy needs we have seen. So classically on solar thermal you have a reservoir and you can have a mirror or some specific adaptation that allow to increase the temperature. So the principle of a simple solar thermal collector is to have an absorber which is selective, very absorbing. At the back side you have a fluid that could be air, water, oil that is collecting this heat. And depending of what you put at the top of the absorber, you are losing more or less some heat, okay, or that allow to increase. Different technology of collector type. So more simple, it is unglassed plastic. So it's like wire, black wire, okay. You can do it in your garden or to have a hot shower. There is industrial unglassed absorbers that are used for swimming pool, for example, if you want to upgrade the temperature. The maximum operating temperature is limited, of course. Then you have glassed metal absorber with black coating, so what we call flat plate covered. You can reach around 60, now there is 70 for water heating and air heating. It's good, and cooling, we will see. Glassed metal absorber, not cooling, sorry. A glassed metal absorber with selective surface, you can reach 90 degrees, so also for water heating and air heating. Then you erase the convective heat transfer when you have evacuate tube. So you can reach until 180 degrees. This it could be used for cooling, okay, with adsorption machine. Then you have non-tracking concentrator. So that means non-tracking. You remember about the concentrator. You have linear parabolic concentrators. That means the parabol are at least tracking on one axis, okay, and you have of a kind of the dish. You remember the parabole with the Stirling engine at the focal, which can follow in two directions. Okay, so tracking concentration with 1 point focus, it is the dish, the parabole, and you can reach 1000, which is necessary to generate electricity with Stirling engine. Okay. Heliostat, so you can reach 100 and 500 degree, and it is classical heliostat if you remember a tower. Okay. If you remember the furnace of Odeyo, there is heliostats that are reflecting on a big parabole that are reflecting in 1 point, and here we are able to reach more than 4,000 degrees. Okay. But it's very rare. I think there's not too much kind of this application. So this is a large range that we can reach in terms of temperature, so that we can find some applications to many fields. Preheating, heating, drying, cooling, generation of electricity. The problem of this technology is not the large range of temperature which is available. It's really nice to have such a large range of possibility. The problem is mainly the cost now, okay? Because it is made with, except the plastic, all need some copper, some mirror, so the price of such an element is higher than a classical PV panel. So even a classical flat plate collector with a glass absorber, selective absorber, heat exchanger, insulation, air tightness to be fully tight, it's more expensive than it seems to be a simple technology, very simple, but it's more expensive than PV because the price has decreased. So here you have some illustration. It is an unglassed PV collector. We have seen solar wall, or it could be plastic also here on the facade. Classical flat plate covered collector and vacuate tube for the application of building. Here you have a nice illustration of very high unglassed PV unglassed solar thermal collector. Okay, you can see this black. It is made with stainless steel sheet all along the height of the tower in order to preheat the air or to heat the air of this tower, which is dwelling apartment. Okay, so this principle, you have a porous solar steel stainless absorbing facade, and you are ventilating this air gap in order to the air to come all along the facade inside the building. So it's a very simple application. It's a more simple application. You can use it also for big space, industrial space, to warm, to preheat the air, or to dry also, because the level of temperature could be enough, could be sufficient. Collector with glass cover, so you have the absorber. The principle is to to transfer the heat that is collected at the level of absorber by a fluid. So there is many studies working on the heat exchanger to increase the efficiency of heat exchanger, to increase the recovering of the heat. Also on fluid, there was also some fluid with nanoparticles in order to increase heat transfer. So many research on this. And also on materials, because as I told you, plate of copper now it's expensive. Okay, even if it is very thin. So to try to find alternative materials that are not so good as copper in terms of heat transfer, but are less expensive. So to find a compromise between the enhancements of heat transfer between fluid and the absorber and the quality of the materials of absorber. Okay. It's a big issue. Some nice integration in a house where you can see that there is also some effort to integrate this kind of connector in the envelope. So this is typically for domestic hot water. Or also there is some systems that allow to have domestic hot water and also heating system inside the house or the building by heating floor. Okay. It is very convenient with heating floor, because heating floor you don't need to have a high level of temperature. You have to be very low, maximum 27 degrees at the surface of the heating flow. So it's good if it's good adapted, but also very expensive. So vacuum tube is more delicate to integrate it well in the roof because of the shape. It is cylinder because they could mechanically resist to the fact that there is a vacuum inside. Okay, so if there is some rain or something, it will not explode due to this shape. So the principle that it depends, there is various we will see. Some are more, the more developed like this, with the absorber in the middle, okay, and the fluid circulation related to this absorber. You have also very simple evacuate tube where the absorber is it is a thin film, a black thin film, which is recovering the inner surface of the internal tube. Okay, and so that means that there is water, full water in this tube. Okay, very simple.
This is a flat plate kind.
Yes.
It's a flat plate added in a bolts.
Yes.
Through heat transfer fluid flow.
Yes, for this, but there is also very simple that are which show in the picture like this, where the absorber is inside the tube, and so in the full tube is with water. So that means that when the sun shines and is absorbed by the internal tube, okay, that will heat the water. The density of the water will change, so like a thermosiphon phenomena, like we have seen with solar chimney. Okay, so all along here, the hot water will go up, and the cold water, which is in the tank, will go down. Okay, so there is a natural circulation, which is made like this. I have tested such a collector even in a very cold climate. I put that in a freezer to see if there was no problem of frozen, because it is water. In such a design, the water which is in the tank and which is going in the collector is directly consumed. When you take a shower, it is the same water that is here that is going in your shower. Okay, so there is no alcohol, no. So the main problem could appear to be when there is very low temperature, but with very low temperature, it's incredible. There was very interesting micro-circulation phenomena. So it was very, very strong. So this is the more simplest technology. You plug in directly in the solar tank, vacuate tube, and inside the vacuate tube there is the absorber. It's a thin layer of absorption, and the water is going inside. And the one with this kind of technology, which is more efficient in terms of heat exchange, so this absorber with the circulation is this kind of tube that you have presented in your lecture, where here you have you are plugging to the heat exchanger with that brings the heat to the tank. So it's more sophisticated, more efficient, of course, but more expensive than this, which is very simple technology. Okay, so very interesting and, of course, more efficient. Thanks to that, you can reach 180 degrees, not with this system, which is more dedicated for domestic hot water, so you will not reach so high level of temperature. But very economic, not expensive. Okay. So what is important also, it is the positioning of this captor, the inclination, the optimum inclination. So it depends of your system. If it is only dedicated to domestic hot water, it's okay. There is no real challenge for the optimum inclination. If your solar thermal is also for another application, solar cooling, for example, or solar heating in the flow injection. Solar heating, it will be very important during winter time, so you have to focus on the winter, okay? So the winter, I remind you, the sun is lower in the sky, so the inclination will be higher. If for system, yes, is for heating, yes, it will be more close than 60 degrees than 30 degrees. If it is for solar cooling, it will be more close from 30 degrees because we want to produce maximum during summertime to cool. Okay, so it's the same kind of preoccupation. What is interesting is depending, do you want to produce the maximum all the time in the year or at a specific period? And so if it is at a specific period for a specific need, you have to focus on the position of the sun in this period. Is it high? Is it low? And also the number of hours of sun per day and so on and so on. Okay. Never forget the final need. Okay. So the efficiency depends on the technology. I said, should we have a collector with copper, with very selective coating, ambient condition, so it's very important. If you have a flat plate collector without cover, that means without glass cover, the wind is very, 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 very important. If there is wind, all what you expect to collect will go with the wind. Even if it's a solar flat plate collector with glass cover, it could be, when there is a lot of wind, could have impact on the efficiency of the solar thermal. The sky temperature, obviously, because your solar collector, it has higher level of temperature, so is emitting with the sky, okay? So it's more delicate, and it's not good for solar thermal to emit. It's good for solar PV to emit radiation to the Celeste volt. It allows it to cool down. It's not good for solar thermal. That means that you are losing some heat. And there is, yes, very important, flow rate, inlet temperature, ambient temperature are parameters that are very important for the efficiency. Some example of absorber. So this is the one that we have developed, you remember yesterday when I was presenting PVT with a fractal heat exchanger. This is the heat exchanger, okay? So it is an aluminium. So you see the heat exchanger, you have different with other kind of aluminium, composite with between aluminium and copper, and even Dualson has made a polymer heat exchanger. Polymer is not very famous for heat conduction, but it's famous for the price. So this polymer was including some particles of metals in order to enhance heat transfer. And the originality is that the price is very low because you can produce it very fastly. And this is a kind of heat exchanger with copper. Okay, so a lot of evolution on the absorber due to the price of the metal and trying to keep a good heat transfer.
For polymer, I think thermal conductivity will be lower.
Yeah, yes, for sure. So they add some particles of metals in order to increase the conductivity of the polymer. This is manufactured as a roll bond. It is a roll bond technology. It is a heat exchanger, the kind of heat exchanger, not the shape, but the kind of heat exchanger that we find in a fridge. In the fridge, inside the wall of the fridge, you have aluminium heat exchanger that have particular shape for the fridge that are made with the same technology. So this technology is called roll bond. So you have two piece of aluminium, two foil of aluminium. In one you are drawing with ink the draw you want. You can have an heat exchanger with your face because you can. It's just printed on one foil of aluminium. Then you put the two foil of aluminium. You heat. Okay, when you heat, there is a melt. It's a connection of aluminium, the two foil, except in place where there is the ink. Okay. There is no mixing where there is ink. So then after you open at the border here where the two foil and you inject air, compressed air. And where there was a ink, it's I don't remember the name in English, but it's okay. And where there was no ink, it stay joint. Okay, so with this technology, it's very funny. You can and efficient. You can draw the heat exchanger you want. Okay, it is called roll bond. So they explained that we were able to have such heat exchanger.
You're doing the purpose of 3D printing.
Yes.
By blowing air.
Yeah, yes, you can. And now, yes, you have 3D printing that can do it. Okay, so regarding a flat plate collector, when we receive 100%, okay, we said 100% of solar radiation, there is 8% which is reflected, usually. Okay, then after you have 15% which is lost here because there is air and there is convectivity transfer. So between absorber, okay, convection, and the glass and out. You have 88% which is emitted outside, okay, by the absorber. Absorber is emitting in infrared, so the glass which is opaque to infrared will allow to keep the radiation inside, okay? But there is a bit loss of radiation infrared. You have also, as you are heating, some thermal loss at the back side of the collector. That is the reason why you have a big layer of insulation in order to avoid heat transfer between the heat exchanger and the back side. Okay, usually, so you recover around 60 to 70% of the incident radiation, depending of the quality of the flat plate. If you have a vacuate tube, it's higher, of course. You are neutralizing the convective loss. Okay. So you have to have big absorption coefficient and low emissivity is good, so very selective absorber. Absorber with high conductivity, if possible. The best is the copper, but the more expensive is the copper. So there is a lot of research to change with keeping the same conductivity and okay, and the roll bond process, I discussed about that. Good thermal contact is important between tubes and absorber, and air and water tightness, it's essential. If you have a leak of air in your collector, that means that you will have humidity that can come in. Sometimes you see that when a solar thermal flat plate collector is bad or is old, there is very often air inlet that appear, and then with humidity, and sometimes you will see some condensation. So you can imagine if you have water condensation on this glass, you lose a lot of energy because water is also opaque to infrared. So infrared coming from could be stopped. Okay. Classical data about this. So when it is a classical representation, sorry, I've got a better, but just to show you the three things. So it's a classical curve of efficiency of a solar thermal. Okay. And this is the difference of temperature between the solar collector and the ambient temperature. And this is the efficiency. Okay. In this this point particular is called optical efficiency. Okay, it's the optical quality of your solar collector. The higher it is, the best it is. Those we call that this range to 100% of efficiency. This gap is what we call optical loss. Okay, this is 100% of efficiency. So the gap with this between this point and 100 is optical loss. Okay. Then when you are going below, it's not due to optic. So the absorptivity, the glass cover, and so on. It is linked to the thermal loss. Okay. So of course, if you reduce this, the efficiency will be better at higher temperature. The classical formula of the efficiency, it's okay, you have seen so this part between this point and 100% optical loss, this part is thermal loss, due to thermal loss. The classical expression is like this. So a coefficient minus what is representing the thermal loss. So the mean temperature, depending on the mean temperature of the solar collector, of the water in the solar collector, and the ambient temperature. Okay, the thermal loss is linked to the difference of temperature between inside and outside. Okay. So multiply by this equivalent conduction coefficient, sorry, and divided by the radiation. To be more accurate, the real one is like this. It's not a line, but it could be a bit curved. So some manufacturers of solar thermal are giving these two coefficients. You have one coefficient here, one coefficient here due to thermal loss, and this one is the same, it's optical loss. Optical efficiency, sorry. Okay? So yeah, it's better. So you have better idea, but I wanted to show optical loss. So okay, and glassed, there is almost not optical loss because there is no glass. So if no glass, no problem. Okay, there's no reflection on the glass, and but you can see that the efficiency decrease very fastly. So it's good for not high level of temperature. Then here you have glassed black absorber. So you see it's not really linear. Very often we put linear, but it's a bit curved. Here it's glassed with selective absorber, and here it is evacuate tube. So the main characteristic of the different technology. Evacuate tube, you have more optical loss because, have you seen, you have a double glass because we need to generate the vacuum. So the loss due to the glass is a bit higher than for the other. But could allow to maintain a good efficiency with increase of temperature. Okay? Yes?
Slope of this curve says that it is a lossy kind of thing. If slope is low, then our system is lossy. But for evacuating collector, it is like a straight line with very less slope.
Yes.
Since there is less thermal loss in this evacuating.
Yes.
Even though there is a temperature.
Globally, there is less thermal loss. Yes.
So is it like that, in spite of the fact that temperature is high, in my tube temperature is very high, and outside it is like ambient temperature.
Yes.
So
Yes, thermal
is
loss is indoor compared to outdoor, so the delta T. Okay, so mean temperature of the collector compared to ambient temperature, and it's right. Here, the thermal loss are very negligible.
okay, so that's because of the
Because
vacuum
you
tubes.
erase the convection.
Yes.
Because one here in the thermal loss, you see convection phenomena because you have air,
Yes.
so it's hot here, and so you have a circulation of the hot air inside that exchange with this glass and generate thermal loss.
And I have one question regarding the efficiency here in previous slide. So can we find some threshold kind of solar radiation by using this formula? Because if the second term minus term is equal to eta naught,
Yes,
then efficiency will be 0.
yes,
So that means there is a threshold intensity solar radiation below that our system will not operate. So it should be more than that. By seeing this formula, so
Yes.
am I right, or there is a misconception?
No. It can operate with small g. G is a global radiation.
Okay. So
Yes.
if G is lesser than this value, let us say I have some value of UL, operating temperature, and
Yes.
ambient temperature. By mathematically, if you are fitting that, let us say this minus quantity is equal to eta naught,
Yes.
then corresponding to that, whatever G we will calculate,
Yes, but
below that-
you have we have to notice when G is low,
yeah.
T will be low, will be close for ambient temperature.
Hmm.
So the both are changing.
Okay.
We will not have a high mean temperature
Yes.
with a G low.
Low.
Okay. So these are moving together, very dependent. Okay. So yes, I agree with what you said, but when G decrease, T decrease fastly also. T
Yes.
mean will decrease fastly.
Mm.
Okay. And when there is no G, there is ambient temperature in
Yes.
the solar collector. Okay.
Okay. Thank you.
Yes. Good question, but yes, T mean temperature and G are very, very related.
Okay.
Okay, some examples here. I found some different technology. The bad thing is that around that, some industry have disappeared already due to the fact that PV is now very inexpensive. It's a paradox. PV was very expensive due to when you look at the PV panels, the technology which is implied is higher than in solar thermal. Solar thermal is quite simple, but the materials that are used are more expensive, and with this range of solar collector, you can just do heat, can just generate heat. So yes, and it's better to sell electricity than to use your own heat. The main problem is the business behind. It's not the need, the answer to the need, because you are able to answer to a lot of needs with solar thermal. But in terms of business, it's better to produce electricity even if you sell it. You don't use it. Okay. So, but it is some example and some coefficient. So you can see, you can directly see which collector has a very good optical 0.82 compared to the other. This one is very well. Okay. And you have also, so this one is very good in terms of probably insulation, which is behind the heat exchanger. This not so good. So it gives you straight an idea of the optical and the quality of the heat loss. Just seeing these two parameters. Okay. Okay. The test for a solar thermal collector are following standards. So, of course, the efficiency is depending of the radiation and of the external condition, so ambient temperature, wind. So, the standards, you have to test it under 1 meter per second of velocity. Temperature and the inlet temperature. So the standards are when you test the solar thermal, you will start by inlet temperature, then you will change the inlet temperature to see how it behaves, and it allows you to determine the curve as we have seen at different temperature, inlet temperature. Okay. one important thing, pity that I can't write. In this kind of bench, it is artificial light, okay, that generate solar, artificial solar. It's not really important the quality of the light, because compared to a PV, it's very important, because PV the conversion around one wavelength, whereas solar thermal is taking everything, okay? But there's one important thing that sometimes people that are testing solar thermal are making mistake. Your solar thermal collector is heated, and it is very important to consider that it can emit infrared near the sky, in the direction of the sky, the celeste volt. Okay? It's very important, because if you don't consider that it is emitted also in direction of the sky, you will overestimate, by this test, you will overestimate their efficiency. So how can we simulate here that this collector is emitted in direction of the celeste volt? You don't see it, but this frame here is for a big glass, which is over. We can see here some reflection. There is the light here. There is big glass here, and there is the solar collector under. Okay, and it is a double glass. It is a double glass inside which there is cool air. Cool air is circulating in this double glass. Cool around 5 to 6 degrees. So there is a cold glass finally that simulates the celeste volt. Okay, so you have radiation, okay, coming from the artificial light, absorbed by the solar collector and so on, and the solar collector is emitted in direction of a cool surface, which is this glass, inside which there is a cool airflow. It is the condition to have a quite accurate evaluation of the efficiency of solar thermal collector in control condition. If you don't do that, you will overestimate the efficiency, because the emission of the solar thermal in direction of the celeste volt will not be taken into account. So you are neutralizing a part of the loss. This, okay, which is 8%. So it was just, but important when you test in a control condition, solar thermal. Okay, so some kind of integration of solar thermal. So you can see this is not integrated. It's the same as PV, huh? Not really integrated, but not so bad, and fully integrated here. Here also you can find like PV, some rack like this in the flat plate roof. Of course you have to be careful of the shadow. It's less delicate than PV. Hein? The shadow effect is less delicate. It's not because you have a small shadow here that it will destroy all your efficiency of the solar. That means you will just receive less radiation, but it's less delicate. But of course, you have to be cautious when you are positioning these two, not to have cell shadow. Here, it's also integration in a balcony. Could be also now vertical. You can see evacuate tube on the balcony. At a bigger scale, the leader, the big scale solar thermal production for coupling on the grid, solar thermal grid, solar thermal distribution is Denmark. They have developed a lot solar thermal and injection on the grid. So here it's not a PV central, it is a solar thermal central connected to the thermal grid of a city. So you can see you have 8,000 square meters of thermal collectors that are providing 15% of the heating and domestic hot water need of 1,000 homes.
All are evacuated tube?
Hmm?
These all are evacuated to flat?
Evacuate tube. And in this way, of course, maintenance and things like this. So yes, Denmark is one of the leaders on this. Okay, so for application space heating, yes, I already said that. Underflow heating, pool heating. Now pool heating, especially in Europe where it is cold during winter, most of the municipal pools are heated and they use solar thermal. So it's one of the good application of this. For the solar thermal for domestic, for example, there is one constraint, which is what we call stagnation temperature. It is also a problem with solar thermal. Is it when you don't use it, it's coming hot, 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 hot. You have to evacuate at a certain stage, or you can see some people put some screen on the solar thermal. So because when you are going in travel or in holidays, the family don't use anymore hot water, and at a certain stage it's becoming too hot, okay? Because it's a closed loop. So there is a system that allow to avoid that. More simple is to have a screen on your solar thermal. The other is there was a drain back system, so you are you are empty all the hydraulic system and store the heat transfer fluid in a tank. Okay, and don't use the solar thermal. And then when you are coming again, you are filling all your loop and use it again. You have also, in terms of maintenance, to change the fluid every 5 years. In Europe, because in Europe the fluid is water plus alcohol, okay, in order to avoid to freeze during winter time. So, and this fluid aging with, because heat and cold and heat and cold, and it's better to, it's suggested to change it every 5 years. Okay. So there is facing that, there is yes constraint that is not in the PV in terms of maintenance. If also you have a leak of water, because it's tube everywhere, it's delicate for the maintenance. So this is in a very big competition with PV, a PV coupled with heat pump now for this. Because of maintenance, because of the price of the materials that are required, and also to install it needs also a kind of expertise. Which show you there was a lot of problem on such installation in France in terms of energy consumption. I will explain you later why. Okay, some example in Grenoble near Savoie. So it's well developed solar thermal for social apartment because it's allowed to decrease the charge of the people that are inside if you can heat like this. So it's a nice here installation of solar thermal for social apartment. And there is still a support from the National Agency of Energy and Environment to push for that, but to push more now a big scale in order to develop heating grid, central heating grid. ADEME is pushing a lot to have a centralized production of heat distributed in buildings, and so it is well supported. You can couple this also with heat pump like PV, but so heat pump in order to increase the efficiency of the heat pump, the global efficiency of the system. So it could be an uncovered solar thermal collector. You just have to upgrade a bit the temperature, and it's quite well. There was also some attempt about that. This is application where you are generating heat for a domestic tank, domestic hot water tank, and also heating system. So heating system on the floor. Okay, it has been well developed in France for heating system. It's quite comfortable. Heating floor is quite comfortable, and the application is also well adapted to that. So this is a classical installation for both domestic hot water and heating of a house. I don't know at what time we have a break. Now? Okay. Okay. So yes, it's interesting if you have a break now because this second part is for cooling. Okay. And this special application for this afternoon, the second cooling. So we can make a break now. Question regarding heating system, solar heating system? By Excel file, you can, yes, because you are plotting the H, yes, and this the position regarding south. So it is azimuth. Yes, and with the formula, yes. No, it's not this. I will show you which data is. This is the variation, of course, because here there's no variation. Can you hear me? I was telling to the... It's okay? Oh. No, I was with my microphone. Ah. It's working? Okay. Thank you. So I will start. Okay, so now we are dealing with solar cooling after having seen the solar heating. I would like first to introduce this. We will work on this principle this afternoon on solar cooling by what we call desiccant cooling. Solar cooling or cooling is very important thing, and it has been developed by centuries and centuries in very hot countries. And one of the more efficient phenomena associated to the cooling is evaporation. Okay, so we can we call that evaporative cooling. That means that if when water is evaporate, it take a part of latent heat in the surroundings that allow to decrease a bit the temperature. Okay. So here you have an illustration of outdoor air conditioning system. It's stupid to say outdoor because it's fully open, but when it is very hot outdoor, you may have seen some thing like this. It's a kind of brumisator that inject very thin droplet of water, a kind of fog that evaporate. Okay, as soon as the thin droplet are outside, they evaporate and allow to cool down the surrounding. Okay, so it's used in very hot country, in open space, in railway station, for example, or even along some paths where it is very hot to walk. You have this kind of injection of thin droplet of water that evaporate and allow to decrease the temperature. Have you also seen this kind of diagram, psychometric diagram, or not? So yesterday, Dr. Pankaj gave you, I think, one. So we will work on it this afternoon to see what is the operating condition of what we call desiccant cooling. Of course, desiccant cooling is not only based on this, because you can imagine here inside, if we were injecting thin droplet of water, at the first stage we will feel comfortable. It's cooled down. But at the second stage, you will feel very uncomfortable, like in a humid tropical country. Okay, humid, hot tropical country. So that means that we are obliged to dry at one stage, to dry the air and to humidify the air. So it's more complex than this simple thing, but the main thing which is behind is evaporative cooling, behind the desiccant cooling. It has been developed, as I say, in Persia, so now Iran. It is here, you can see wind tower, okay? So wind catcher, we can say. It is a very interesting tower that don't use chimney effect as yesterday, but when the wind is crossing this tower, there is some tube where there is injection of air inside, collected, the wind is collected, and there is some tubes that are open, and the wind which is crossing is inducing a pressure loss that allow to the air to be aspirated. So there is a double operating here tubes. One are injecting, catching the wind, injecting. One is aspiring, exhausting, allow to exhaust the air. And what is here behind? It is water tank. Okay, water tank for usage, okay, of the water, but it is also used to cool the air. And they have developed very interesting underground tubes in order the cool air is distributed to the house. There is still this kind of system of evaporative cooling. You can see also in Romanian it was almost the same. There was inside the house some basin, fontaine, okay. In Egypt also you see all around the building and sometimes inside the building some basin of water. It was nice, but it was also for cooling because the water when evaporating is cooling down the ambience, okay. Here another example of this evaporative cooling in Mali. So here is a house. Here you have a kind of linen at the top. During the night, people are putting some water, okay? So the linen is completely full of water. During the day, this is drying, so they evaporate, and the cool air is going down in the house because due to this evaporation, and so it's allowed to cool the house. Interesting. That has been also developed in a museum in the United States, where you have also wind catcher. It's a wind catcher, and here you have a kind of system of basin. There was evaporation and injection in the building, so it's passive, free cooling, okay, by evaporation. I like this phenomenon. So in reality, we will deal with this system. It is the traduction, the implementation of this principle in HVAC system, okay? So how it's working? As I told you, so here you have the house, okay, or the building. You have a double flux management of air mechanically, okay. You manage the injection of fresh air in the building, and you manage the exhaust of air, okay. As I told you, if we want to humidify the air by evaporative cooling, first we have to dry it. So before the air is going inside the building, it is crossing what we call desiccant wheel, okay? Desiccant means dry, okay? So it could be salt. If you want to have an analogy, it's a kind of salt. Okay, you see that salt with humidity, there's a good match. Okay, so the salt, it's reality more silica gel, has a good attraction with humidity. Okay, voilà, battery, and so catch the humidity of the air. Okay, and then at the outlet you have dry air. Here you have an heat exchanger, classical heat exchanger. It's allowed to be cooled by the air which is exhausted. In principle, inside the air is cooler. Okay, so the air that you will extract is cooler. The air that you will inject is hotter. So you have a heat exchanger to allow to cool a bit the air before it's going in. And then here you have the injection of humidity, so evaporative cooling. So it's here that you cool down. Okay. Why There is also a humidificator here for the air exhaust. What could it be for? Okay, so it's for air inlet, and this is for air extraction. Why we are using also here evaporative cooling? We are using here evaporative cooling in order to decrease the temperature of the air, okay, before the heat exchanger. Like this, the heat exchange is better, okay? We decrease the temperature of the exhaust air is cooler, but we decrease it again in order to increase the delta T here, so to allow to have more heat exchange, okay? Then we are heating this air, and it is here that the solar thermal is coming, okay? We are heating this air just before crossing the desiccant wheel. Why? Because we want to dry the desiccant wheel, okay? Because the humidity is collected here, we have to get rid of. If we don't get rid of this humidity, at the certain stage, the wheel will be fully saturated. And if the wheel is fully saturated in humidity, the process can't operate anymore, okay? So we are heating the air before crossing the desiccant wheel in order to evacuate the humidity, okay? And to be sure that here we can catch humidity again. So it's something that is running very slowly. It is a wheel which is running slowly in order to catch humidity and to get rid of humidity. So it is the principle of desiccant cooling. So solar thermal cooling by desiccation. Okay? So you can say that finally the solar thermal is not used for the building. It is evacuate. Okay, but it is necessary.
But here we can control humidity as well, right?
Ah yes, here. Yes, yes. Due to that, yes. And it's important to control the humidity, because if you don't control it, it could be very uncomfortable inside, or the process could break down. Okay. So it is a modern traduction of evaporative cooling that has been used since centuries. But because we are in a closed building, in the past there was no windows, it was fully open. Okay, so no problem to inject, to have a swimming pool in your house, because there was no windows, it was open. Okay, so if there is evaporation, at a certain stage humidity is going out. But here we are closed. So if we inject humidity, it will become too humid and uncomfortable. Okay? So it is the main principle that we will study this afternoon. Okay? And what will be our target this afternoon regarding that? Compared to classical cooling system, what will be our objective? It will be to see if we are less consuming electricity than a classical heat pump, which is very efficient in terms of consumption. Heat pump efficiency could be 300%. Okay, so it's very efficient. Should we do, with thanks to this system, is the electricity power is lower or not? And the other point, what amount of water we are consuming? Okay, if I want to cool down this amphitheater, do I need a full truck for half a day, a full truck of water, or should I need a small tank of water? Okay, it's very important. Obviously, we will see that it is very efficient in terms of electricity. But you have seen the complexity of the system. It is very delicate to control, okay, to manage. We have to be sure that all the humidity that is taken here is fully extracted, is not partially extracted, is fully. Because if it's only partially, after a couple of hours, it will saturate, okay? So the humidity that is collected here has to be fully extracted. If it's not the case, the system will break down after several hours of operating. Question? Oh, I like a lot this system, but it's very complex. Finally, the physical phenomena that are behind are very simple, but after to put in practice and to control this system, it's very delicate. Okay.
I have a few queries and then scope of doing some kind of combined research. Here in this part of the country, during the summer, we reach a temperature of about 38-39 degree, but humidity is close to 90%. So it is very, very uncomfortable. Every time you will sweat. So those who can afford, they can buy commercial air conditioning systems, which is operated by vapor compression refrigeration system, and which uses refrigerant. Now, can we devise a mechanism which is lower in cost, so that the people who is living in the countryside, they can also afford with this kind of system. So what you need to really do is to reduce the temperature, reduce the humidity. Temperature is fine, it's 35, 34, 30 or maybe 38. That is okay if we could reduce the humidity.
Yes,
so,
it could be possible. It is like a classical cooling system. In some country where it is not so hot but very humid, it is used mainly to dehumidify. We will see that this afternoon, that it is the equivalent. Of course, all this loop is the equivalent of a classical cooling system. Of course, if it is not equivalent, it's not good. So we will see this afternoon what a classical system is doing and what are all the transformation to do the same thing as a classical system. But it is right, when it is too humid and not so hot, it is used to dehumidify more than really cooling. The more important is to dehumidify.
Yeah, but at the same time, that has to be economic. That we need to check.
Yes, economically, it's more expensive than a classical. It is the same parallel as PV and solar thermal than heat pump and this.
So where we are dehumidifying the air by using the solar collector or solar energy, so their material will be a major important thing, because the air is containing water and we have to dry it. So it should be like the material will be a challenge, that it should not be corrosive or it should not be deteriorate after certain time, because that will lead to a efficiency degradation of the system.
Yes, you're right. We will see this afternoon if we have time. I don't know if we progress. It will depend of our progress in the tutorial. But of course, there is at the backside a need of thermal storage in order to ensure stability when there is variation of solar energy or no solar energy.
Yes, yes.
So in the whole system, I will propose you this afternoon, if we have time, to study the system, and then we will design the solar thermal storage.
Okay.
Okay, it's very important.
Thank
And it is the same. So for such a system, if we will take in consideration an amphitheater like this, a bit bigger, and what autonomy we have to choose? Will it be so? It's not reasonable to say 2-3 days like
Yes.
in PV, because there's no sense to store solar thermal for 3 days for cooling. And usually, when there is no sun, you need less to cool.
Yes.
Okay, so it's related to the cooling needs are fully related to the sun. So it will be at the scale of the day. Okay. Imagine this morning it is sunny, okay, and this afternoon it become cloudy, but it will still remain hot. Okay. So typically for such a system, the design of the solar storage. The storage will be around 3 hours to spend the afternoon in the same condition of okay. So we will see that. I hope we will have time to deal with also the thermal storage with phase change materials or water. Okay. Other question? Yes.
Okay, thank you. Inlet air cooling system. No, second, yeah. When air is coming from outside,
Yes,
and
it's here.
then it will be cooled.
At heat exchanger.
Heat exchanger. Next, from here,
Evaporative.
cold air will come to building, and again from exit. Again,
Yes.
it will be cooled.
Yes.
So, the air coming from outside to the building, its density will be lighter than the air going from up above. So due to density difference, the cold air from above will go down.
Yes. Well, this is just a picture of, and it is not natural. It's not natural ventilation. It's mechanical. So when you extract it, whatever, if it is down or you extract the air, so it's mechanical.
But because of density difference, if that air comes down, it will facilitate cooling, because the air coming from above side, it will be more because
But here in this HVAC system, there is no connection, no
Okay.
direct connection
All right, okay.
between air here
Okay.
and air down. It's fully separate.
Okay.
Of course, because there is also pollutants. When you extract the air, it's to have a more to improve the quality of air inside the building. Yes, because we are all injecting some pollutants. There is some pans that are injecting COV and so on and so on. So you renew the air because you want to clean the air inside. Okay, so there is never direct link between exhaust air and new air. Okay, just the link is by heat transfer here and by the desiccant wheel here, but there is no connection between two tubes. Okay. Yes, it is a double flux system that are now compulsory in new building in Europe.
Okay.
This system is double flux, that you are mastering the inlet
Okay.
and you are mastering the outlet, because the building are fully tight and very well insulated. Okay, and it is allowed during winter time. This is heat exchanger during winter time, allowed to recover a part of heat which is rejected outside. During winter, it's also operated. Of course, you erase the humidity, or you can use it if you want to inject humidity, because the air is dry when it's cold outside. But this heat exchanger is still used during winter, because the hot air which is coming from the building, which is extracted, is exchanging with the cool air which is coming in. So the double flux system plus heat exchanger
Mhm.
is now compulsory in every new building in Europe
Yeah. Now I understand.
because we want to master exactly the loss, energy loss.
Okay.
Okay. So we'll see what it will imply on the in terms of transformation. Just, it is very simple transformation. It is simple heating, simple cooling, or evaporative cooling. And evaporative cooling is an adiabatic transformation. Okay. So we'll see it's some series of very simple transformation. Okay, so this is an image of this installation. So you have the air inlet, the desiccant wheel. Okay. Here you can have also a heat exchanger, rotative heat exchanger, and then you see the way to humidify. There's different way. You can have a kind of sponge. What we see here, a kind of sponge with water, and the air which is crossing this sponge evaporates the water. You can have also some kind of sprinklers that injects very small droplets of water. Okay. Could be, yes. Then you have two other category of cooling system. So we have seen desiccant cooling, okay. There is two others which based on the sorption phenomena, okay. So there is absorption machine or adsorption machine. It's just to recognize what kind of media are implied. Do you know the sorption? So it's implied two media. Okay. For example, in the desiccant cooling, when you have salt and humidity, when they match together, it is what we called adsorption. Okay, adsorption, that they have a special relationship, very strong. We call that thermochemical attraction. So they mix together, and this reaction generate heat. Okay, when you have salt and humidity, when they match, it injects some heat. Okay, it's warming. At the reverse, if you want to recover your salt, you have to heat this mix. Okay, you have to heat the mix, and then the humidity will evaporate and separate from the salt. Maybe you have seen this kind of, if you leave your salt like this open in a humid atmosphere, after 2 days it's a block like this because there is absorption with humidity, okay? And during this absorption phenomena, if you are putting some flux meter or thermocouple, you will have seen that there was injection of heat. Then when it's finished, you have a block like this, a very strong relation. If you want to separate again, you have to inject heat to warm that. And then humidity is separate. We call that desorption. Okay. So sorption machines are based like this. Two couple, two media, when they are close, they are attracted and mix together and release some heat. Then it's a very stable mix. When you want to separate again, you injected some heat. At a certain point, one of the two will evaporate and separate. Okay? So this principle is used to store energy or to generate cool. Okay? When you want to separate that you have to inject some heat, okay? And it is during this phenomena that you will take some heat. If you inject some heat, that means that you take some heat, okay? So this principle, and when they mix together, you give some heat, okay? So you are heating in one sense, cooling in the other sense, okay? So it is the principle of sorption. When it is a solid, like the salt, plus humidity, we call that adsorption machine. Okay, the more common adsorption machine is not with salt and water; it is with zeolite. Zeolite, it is solid materials, solid porous materials, plus water. Okay, zeolite plus water. It is adsorption machine, so it's a solid. You bring humidity, they mix together, inject heat. When you want to separate, you are heating them and separate. Okay. Adsorption machine is solid plus liquid or gas. Absorption now is the same phenomena, but it is between two liquid, or one liquid and one gas. Okay. Example, the very efficient couple of absorption is ammoniac, we said, ammoniac plus water, okay? The same. When they are closer, they mix very well and generate heat, okay? When you want to separate, you are heating and there is evaporation of water and it's separate. You have also a bromide lithium plus water, okay? So this kind of machine is called absorption machine. Ab, you recognize it is liquid, or ad, you recognize it is solid plus liquid. Just the main difference, but the physical phenomena that are behind, we call that thermochemical reaction, are very similar. Okay? So it is well used in storage and also used in solar thermal cooling. Finally, you have all seen what are the main components of a classical cooling system, heat pump. You have four main components: evaporator, condenser, pressure loss, compressor. Okay. The objective of this machine, adsorption and absorption, is you have the same three components: evaporator, pressure loss, and condenser. And the principle of this machine is to replace the place where you are consuming electricity, so it's replace the compressor by the equivalent with this phenomena. Okay, so if I had a classical machine, cooling machine, I get rid of compressor and replace by different transformation that do the equivalent. Okay, so there is on the four classical elements that we see in a cooling system: evaporator, condenser, pressure loss, and compressor. You get rid of compressor and replace by transformation that replace this mechanical compressor by a thermochemical compressor. Okay, it's just to give you an idea of this kind of machine. So it has been developed since a long time. At the beginning, this machine were developed. The bring of heat was not solar, was made by combustion. These machines are existing since a long time. And they were using a burner that brings the heat. Okay, so you have fridge, absorption fridge, that have been developed since the 80s. Used, for example, in hot country to design chambers dedicated to the conservation of medicine, for example, where you need, yes, to have a cool temperature, stable temperature. In a camper van, when you have a fridge that you are not connected to the grid and not PV on your roof, it was a burner. It was a small burner fridge. Okay, so the heat that is necessary to prepare was brought by burner. Due to the fact that why not bringing this heat by solar thermal, it's a good idea, but it's also has induced some issue regarding the stability. As I was telling this morning, thermodynamic machine don't like instability. They are very efficient when they operate in stable condition. Okay, so the problem with solar energy is that could fluctuate, variable, and so on and so on. So the challenge was how to maintain a stability to have a good efficiency, a good thermodynamic efficiency. Okay, but this kind of machine was existing since a long time. With the heat was bring by a burner, and there is still. For absorption machine here, the surface of solar. So first you have to very often have vacuum tube. Okay, you need to reach at least 130, 140 degree to heat the couple in order to separate. Okay, so classical flat plate collector is not enough. You need that kind of technology. Just to give you an idea, if I want to cool down hotel of 5 floors, you have to recover the full roof of this kind of solar technology. So it's equivalent to 1/5 of the surface. Okay, I'm clear on the. So just to give you an idea, if I have a full roof, I can cool down 5 floors. So it's an important surface. That means that if you use it only for cooling, it's delicate. Because what to do when you don't cool? Okay, so usually it's well adapted for buildings that have need of cooling and big need of hot water. So hotel, because there's shower, and hospital. Okay, and more developed application in Spain, it was for this kind of building. So you need to cool, and you need hot water. Okay, because if not, what to do about all this hot water? It's delicate. So well adapted for hotel. So you see that there is some installation that installed since a long day. It's quite stable after. The price compared to PV, we come again to the price that makes that this is not so well developed now, because if you imagine that you recover the full roof of the hotel of PV, you can cool and use electricity, so the same challenge each time, but in terms of technology it's very good and interesting, because it is when you have sun that you need cool, so it's good. Okay, but it has to say that it is a big competition in terms of business with PV.
This is more sustainable.
More sustainable, and if you very well adapted if you need to cool and hot water. So for some typical building or even industrial building where they need a lot of hot water and to cool, it's very well adapted. And question, it is clear the principle which is behind. So absorption and absorption is the same. So here it is a principle, so it's absorption, we will see maybe later, but it could be used for storage also. Huh? So this principle, when you heat this kind of couple of media, so you injected heat by sun, by solar energy, you separate them and you can keep them in two different tanks. There is no loss, okay? No loss because it's not sensible heat. There could be in two separate tanks like this at ambient temperature. It is when you put them together again that they will release the heat that you have stored when you are injecting solar energy. Okay? So you have this option. So when you are injecting heat, you have this option. You are separating the two body. The water vapor is in one tank and the other in the other tank. There is condensation. Then it becomes liquid. Then you can mix again and so this is my machine. Okay, so you can recognize that there is a condenser, classical in a cooling system, evaporator. I don't know the name. Where you generate pressure loss. It's the detender or what is? You have four main elements. Expansion. Okay, so that allow to decrease the pressure. Okay, so this and usually in a classical cooling heat pump, this is compressor. Condenser, expansion room, evaporator, and then you have compressor. And it's run like this. Okay? So the compressor is out and we replace by this. Okay? So where you have the injection of solar energy at the desorber level, so you are heating the two couple. One is going to the vapor is going to the condenser, so it could be water vapor. The condensation release a part of it. Okay. Then you have expansion van. You are going to the evaporator. This take a part of it, like in a classical heat pump, and it is here, so that you are generating the cool. Okay. Then it is the liquid is then injected, combined with the pure solution when it was separate, and then come back to the desorber, and so on and so on. So it is the principle of this adsorption or absorption machine. So this is more absorption machine, and the solar energy is bring here. Whereas you take the heat, you cool here. Okay. So it is a reverse process. Here you have some elements. So silica gel plus water, it is also what is used for desiccant cooling. So it is solid plus vapor of water. And you have also activated carbon plus water, zeolite water, calcium chloride, zeolite plus ammoniac. Okay. So different couple. Now it is an adsorption machine. So it's more delicate because in absorption machine you can make the fluid circulate as you want. You can recover. With adsorption machine, that means there's one solid and one come liquid and vapor and liquid and vapor. So you can't put the solid in one place and then displace, and so it's fixed. So it's a kind of a block like this, okay? And you have a system that in at the top we imagine a kind of tank, okay, with a porous media, okay, fully saturated in water. Okay, like volcanic stone, or zeolite water is the same. So fully saturated at the beginning. You bring heat at the top of this tank. Okay, what will happen? In the zone where you are heating, at a certain stage, the water will become vapor. Okay, and will be desorbed. Okay, so this you are drying finally the porous solid media, and the vapor naturally the vapor is leaving. Okay, then you bring the vapor in the condenser, the same element as and at the condensation point when the vapor is condensing it generates heat. Okay, then you have the pressure loss chamber here to go down in pressure, and you arrive so at the evaporator. Okay, and so the evaporator of course is taking some heat. You have vapor which is going naturally. This is a picture of natural, so which is going naturally to the porous media, okay, and then saturate again this, okay. So you have the two stage, condenser, evaporator, then going then again, okay. So when they mix together, here at that stage, it's release some heat. So it's working like this. You inject solar energy here, separation of vapor, going to the condenser, generates heat. So you can use it for heating the water, for example. Going to pressure loss, then evaporation, that takes some heat, and naturally going to the absorbers. And when they mix, they melt, they meet together again, it's release some heat. It's very interesting because there is absolutely no electricity consumption. No need, okay? Whereas here, you need to have a small circulator that bring the fluid in one place to bring to another place, okay? But here, it is fully passive, automatic, without electricity consumption. That is the interest of this machine, adsorption, because all is natural. You are heating it, the vapor naturally is exhausted, okay, go out. Come in the condenser, then you have pressure loss, evaporator due to the pressure loss, okay, that takes some heat, and as it evaporates, it's going up, okay, to the tank. So very interesting also, not so developed, unfortunately, but there is industrial product. The more efficient in this kind of machine are Japanese. Okay, and there is industrial manufacturer of such a machine, and the best are Japanese. But it's very interesting because it's fully autonomous. Just need some heat from sun, and the circulation and the pass of the one of the media is natural. I like also this. Do you have any question regarding absorption, adsorption? Yes?
Means by giving this one input in that first diagram, we got here two outputs like heat extraction in the evaporator and the TCS. So is this possible? Just by giving one input and we got two objectives like it may disobey the second law of thermodynamics or like.
What?
We also got heat equals here, no?
Yes?
Means we adding the heat at first, and in second round, here we add first extract the heat
Yes.
from the room. Okay. So first objective is we got, and simultaneously we also got heat here. That's why.
Yes, we can then after try to 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 enhance this heat which is released, for example, for heating some water. Generally, you try to recover a part of this heat which is lost. So for heating for domestic hot water, for example. But it's just to show you two different pictures, but it's permanent operating. It's keep on operating like this. Here, ejection of vapor. There, vapor is coming back, and so on and so on. Okay. So vapor is coming back. The mix, that as it is porous media, it's coming naturally to the top by capillarity, then extracting again. So it's a permanent operating condition. And so you can, of course, try to use this part and this part also for overheat. Okay, whereas the main objective is here to cool. The main thing is this. If you want, if you identify your cooling needs, it is here that you, and then you're designing all the other due to this need lab here. Okay. Okay. So for solar heating and cooling, one important thing, as I previously said, it is also the storage to maintain stability or to be able to answer to the need when you need it. And it is a problem. For cooling, it could be okay. For cooling, as I said previously, generally you need to cool when there is sun. So it's not a real problem. The main problem is to maintain stability of the process. And to maintain stability, you need to have a bit of thermal storage to have this bump effect if there is sun variation. For heating is delicate because usually you need heat when there is lack of sun. Okay. So here it's an illustration on a whole year. Okay. I show you some installation where you are coupling solar thermal for domestic hot water and heating system. Okay, floor heating system. This is this kind of house. Okay, in Chambéry, in my place, in winter for whole year. The system that is designed here is for heating and producing domestic hot water. Okay, so this is the months of January, February, March, April, May, December. So in December and January, it is here that it is the coldest months and the months where the number of hours per day is the weakest. Okay, so you can see in blue it is my solar thermal production. In red it is my needs. Okay, so you can directly feel that for solar thermal there is a phase change between what I can produce at the maximum. I don't need. I just need. Why there is still a red bar? Because it's my domestic hot water. Okay, I just need domestic hot water, but the heating system is out. I don't need to heat my floor, and so I'm producing the maximum in July. Potential is July, but I just need that. Whereas I need a lot here in the winter time, but I can only produce that. Okay, so it is for that the thermal storage is essential. And it could be essential between night and day, between one day to another, but at this scale could be also interseasonal, okay, to long-term thermal storage. And so it is the reason why thermochemical thermal storage is interesting, because as I told you, when you are injecting heat in your two media mix, you can keep them in two different tanks at ambient temperature. Okay, when you want to recover this heat, you just have to mix them. Whereas the other way to store, you are losing some energy, and so I found this very interesting to see the problem of phase between your need and your capacity to produce. So there is three main ways to store energy. The first one is also developed for centuries and centuries. It is sensible heat. You are heating a body, okay, and when this body temperature is increasing of 1 degree, you know exactly the energy that you give it to him. It is density multiplied by the volume, or the mass multiplied by the capacity heat, okay, multiplied by delta T. If you are increasing of 10 degrees, you know the injection of heat that you have done. When this body is cooled down, okay, losing 1 degree, that means that he give MCP T, okay, delta T. So it's linear, it is sensible heat. The more efficient media is water, which has a very good capacity of storage, but of course limited by the temperature. If you are at 1000 degrees, you can't use water, okay? So sensible heat, that it is water, oil, concrete, could be a solid. You are heating a big block of concrete. The ground also, you can inject heat in the ground and extract it also. Then the second is latent heat, so phase change. Phase change material could be a solid or it could be a liquid, but very often it's around materials like paraffin, okay, a mix with paraffin and things like this. So you inject some heat, they are melting, and in order to melt, they need to absorb latent heat to make this possible. And when they are becoming solid again, they release this heat as latent heat. Okay, and the last one, it is sorption, as I just described. It is also used for a long-term thermal storage. The advantage between each technology is the density, okay? And it's interesting because if you increase the density of storage, that means that you decrease the volume of storage, okay? So if you want a long-term thermal storage, with sensible heat, it will be enormous. If you use phase change material, you can divide the volume by 2, okay? If you use thermochemical, you can again divide it by 2 or more than 2. So at the end, you reduce the volume. So the same amount of energy that you have stored, you can reduce the volume, okay? The problem is that the maturity. Sensible heat storage is very well known, very mastered, and no problem like this. Phase change, there are still some issue, especially in the aging of the materials, because there's also a limited number of cycles, like in a battery. Okay, you are melting, you are becoming solid, melting, solid. This kind of materials are aging. And thermochemical, it's also to find the best material, but it's also to be able to master the reaction. If we imagine that my two stock of different media. If I want to take only a small shower, how should I combine them not to induce the wool reaction of my wool stock? I open my things, take the shower, and I will lose all my stock of energy. So it's more to how to give proportionally give back the thermal energy without generating the wool reaction. Okay, but and also the use for building application is to have safe materials. Okay, there's many possible materials, ammoniac, water, impossible to imagine to have it in your house. Okay, if there's a leak or if there's a leak, you can be attacked by ammoniac, and if there is a fire, it will imply a big disaster in your house. Okay, so there is also need to have safe materials for human application. So big families, so we will see several. To have an idea of density, so for sensible heat, so it's in French, but you can understand sensible heat of in water, the density is around 60 kWh per cubic meter. You can double the density with a phase change material. The main issue is to be able to select the good phase change temperature. Okay, because we'll show you that if you don't, phase change material is not a guarantee to have a best efficiency. If you made a mistake in the evaluation of the good phase change temperature, you can store less than with water. Okay, and then with thermochemical, the density could be between 200 and 500 kilowatt-hour per cubic meter. So it's very interesting to reduce the volume of storage if you want to increase the autonomy. Okay. So different way, different materials. So sensible heat, as I told you, is very simple. Mass, its capacity multiplied by delta T. It's fully linear. So when you inject this energy, the body will increase of several degrees and so on. So we are using water, concrete, oil, and gravel and water for underground storage or big time scale. Okay, so domestic, usually the surface of panel only for domestic is the more common, as not to be so important, so around 1 square meter per inhabitant. The more simple is this kind of collector. Okay, so with operating without electricity, with thermosiphon phenomena, as I previously showed to you. Usually you have the tank which is on the roof also. Here some image. We will never see that in a country where the winter are cold, okay? Because here the solar tank is outdoor, okay? And in a house, it is a more deperditive component, okay? Because it is a place in a house where the temperature difference is more important. Inside your tank, you can have 80 degrees. Outside your tank, if you are inside the house, you have 20 degrees, so you have 60 degrees of difference. If you put it outside, in winter, in a cold country, you have 80 degrees inside, and you can have -10 outside. So 90 degrees of difference. So you imagine the weakness of insulation that you will have to put in order to avoid loss. Usually, it still remains the more deperditive component in a house because we don't put 30 centimeters of insulation around the tank. But it is the place in a house where you have the more big gradient of temperature between inside and outside, so most deperdition, it is the tank. So it is well adapted for country where during winter it's not so cool. Okay. We have more this with external flat plate collector and a thermal storage tank which is inside in order to avoid to give too much calorie to the environment. The other advantage of this, it is the orientation. Okay, here it is horizontal. This is vertical, and it is the main parameter of efficiency of solar thermal storage, because in this configuration you have thermal stratification. Okay, when you are taking some hot water, the hot water is taking at the bottom, where the hot water is hotter. When you take hot water, you inject cold water for the grid. Okay, so what will happen? It is the cold water will progressively go at the top when you are using your solar tank. Okay, so there is a kind of piston effect. It's pushing slowly, 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 slowly. So in terms of capacity of human, you can use 90% of the thermal energy that you have stored. Because of this piston effect, there is no mix. Okay, here you can have 20 degree, 25, 30, until 80. Okay, so it's well stratified. That means that the cool water, when you are injected and you're extracting at the top, will progressively come without mixing, so that you can use 80% of the solar thermal energy that you have stored in your tank. Here, there is also thermal stratification, but only on this 8. Okay, it's the same. When you take solar hot water here at the top, you are injecting new cool water at the bottom, and here the mix is very fast. Okay, you have no piston effect, and as soon as you are injecting cool water, it will mix. So you are not using 90% of the thermal energy that you have stored. It's decreasing very fast. So if you want, for example, to compare, you can take a shower during 40 minutes here. Here, after 10 minutes, you will feel that it cool down. Okay? But it's not a problem in hot country, because in hot country, you prefer to have cool water when it's very hot than very hot water. Okay? So that's why it is developed in hot country and very efficient for this country. In France, there is a Réunion Island near Africa where they are using that a lot. Okay, it's inexpensive, very efficient for local need. But this is very important, yes, thermal stratification in order to have benefit of the whole capacity that has been stored is very important. Okay? So this is a classical installation of solar thermal. You can also couple this to a heating system. And so you have a heat exchanger at the bottom that will heat, and you can have auxiliary. So when there is no sun, you have to inject heat to have domestic hot water. So usually in France it's electrical, okay, but in some country it could be with gas burner or things like this. So to complete. And you have a circulator and so on. So then to choose the temperature that you want at the end, you are combining this hot water with cool water to have the right temperature, expected temperature. One thing which is really important also, and it was my remark when I say in France, there was an audit about this kind of installation and we find that there was a lot of problem. It is, for example, to be able to measure the temperature at the outlet of the solar thermal collector and to see if the temperature is lower than the temperature in the tank to stop the circulation. And there was many installations where this kind of sensor were out of service. Okay, so that means that it was running even during the night. During the night, the solar thermal collector will be hot because it will take hot water from your tank, and so will emit a lot of radiation with the sky, the celeste volt. So that means that during the night you will empty your resource of energy which is in the tank, but you don't see nothing, because if the temperature is going down, auxiliary will take place of the solar collector. So there was a lot of energy consumption due to this system that was supposed to make some economy. And the classical people living in the house will not check if they are consuming electricity or solar thermal. They have hot water. They are thinking that they use hot water coming from the sun. Mainly, if this is not working, it's mainly coming from the auxiliary. Okay? So it has to be very, very important to check that everything is working in order to have not the reverse. Finally, it's the opposite. You are consuming more energy because you are extracting energy and to give it outside. Very important. Sorry. Okay. If you want to optimize with thermal stratification, depending of the outlet temperature of the solar thermal collector, there is some sophisticated tank that allow to inject the water at different level in the balloon, in the tank. Okay. So there is a measure of the temperature around the height, and if you are going out at 50 degrees, it will inject the water at the level where it's around 50 degrees in order not to perturbate to all the stratification.
You need then a lot of controls.
Yes.
A lot of control you need and thermocouples.
Yeah, yes.
Sensors.
It's important. Yes, because you can have, yes, a loss of efficiency.
How many of these tubes are from the collectors?
So they are coming from the collectors, yes. Okay, so another way to have sensitive short-term storage, it was some houses that were developed in the 80s, but at that time, unfortunately, the insulation of this house was not good. So this system was finally not so developed, but it is to use kind of greenhouse, to generate hot air and to inject underground on stones. Okay, so and during the night to make the ventilation going underground to take the heat that has been stored on the stones to heat the house. After there was some development with phase change materials, with sphere of phase change materials. We are injecting it underground and then recover. I like also this system that now is started again to be investigated, because now the houses are more insulated. So it's interesting. But when it was firstly designed, there was too much loss and finally weak bring of this system compared to the energy consumption. It was very important because air. So it's an example. So now I'm also giving as a lecture to my student. It's a kind of porous media, okay, and you are recovering a part of it during the day. So we compute in order to have an evaluation of the temperature of this bed of stones, okay, and capacity of storage. When we are going at the bigger scale, because sensible heat, it could be at the scale of a house, okay, domestic hot water, heating, but of course at the time to seasonal storage. As I told you, usually we are producing a lot during summer and we need a lot during winter. So at the bigger stage it is underground, it is could be swimming pool, like a swimming pool, a big water balloon, but generally it is a mix with a gravel plus water, okay. Or more and more fun is to have some pillars so that inject some heat in the ground. Of course the ground is not very well insulated, so you are losing some heat, but you can store a lot heating the ground and then extract this during winter time when you need. Okay. Example. So it's a real in Germany here. You can see it's after they will build a new building at the top. It is all underground of the length of the building. Okay. It's a kind of swimming pool. You can see the scale. Here you have an engine. Here you have a man. Okay. So just to give you an idea of the scale, it's a big tank where there's a mix between gravel and water. Usually. So typically this is for inter-season storage. You are injecting a lot of heat during summertime and take it during winter. Okay? So you can imagine in terms of maintenance that you have also to check that the civil engineer, civil structure is okay, and so on and so on. So example here is a 12,000 cubic meter of storage, and the same here. Or you have now this kind of systems that are more and more developed, less expensive, is to make some borehole and to inject the heat by the circulation of water inside the borehole in the ground. Okay, borehole that could have 40, 50 meters depth, and many boreholes. So at the scale of a district, each building that are generating heat during summertime are injecting underground, and then it is the reverse circulation for winter. Okay. Example here, it's in Zurich. It is hybrid also photovoltaic thermal collector that are used for both electricity generation and injection of heat in the ground. And so there's a mix between electrical, thermal. Now, regarding latent heat, as I told you, the temperature here, the energy which is stored. So it is linear when it is sensible heat. When it is not sensible, when it is latent, you start to heat, to inject energy, okay, at a certain temperature, phase change temperature. You have a big shift, a big gap, which is related to the latent heat of the phase change, okay? And then, when, for example, it's fully liquid, it's behave again like sensible heat storage. sensible heat storage when it is solid. When it reaches the phase change temperature, it melts. Big storage of heat due to latent heat, and then it behaves as a liquid that you continue to heat, so like a sensible heat storage. Okay, so it is here that it is interesting. Okay. So all the family. Some example here that we can take this afternoon if we can reach the storage design. So usually you have two. You can have two heat mass capacity when it is solid or when it is liquid. So 1 and 2, and also the example of latent heat. So for the sensible heat, it is MCP delta T. For the latent energy, it is latent energy multiplied by the mass only. It is at 1 temperature. So this is by kilojoule per kilogram. And then again, when it is liquid, it is MCP delta T to have an evaluation of the energy that you are storing. Okay. And so you have also for higher temperature here. Of course, it is for concentration, solar thermal concentration application. When you reach 800 degrees, you can't use any more paraffin, water, and so on. It is some specific materials, usually more or less dangerous for the environment. So we will not find that directly in a house or in a district scale. It is dedicated to solar power concentration. Okay. It's okay? Question? Okay, so this regarding phase change material now, there is try to find new kind of non-paraffin compounds, because in the paraffin there is at the backside petrol. Okay, so now try to find more eco biosourced materials like fat of animals, for example. It's phase change materials. They try to investigate many different new, better eco-friendly materials. Okay. So this is the main family. Yeah, here fatty acid, or to try to investigate. Yes, more. Okay, so it's a main characteristic. When you are with salt, so it could be dangerous for environment. It could be also very corrosive. So it's important to check the volume of storage for the big power station, solar power station, where there is big tank of this kind of salt. Okay, so there's a lot of range, of course, of temperature, low temperature, which is more for application in building, medium temperature, and high temperature, which is dedicated to solar thermal concentration. You can have mix between sensible and phase change. For example, you can, in your domestic hot water tank, reduce the scale of the tank by mixing water with this kind of nodules. Okay, so this is a sphere which is filled with phase change material. You could put that in your solar tank. It will allow to reduce your tank. Okay, we'll see that this afternoon. And so it can evolve One thing to be cautioned when you put the phase change material in a finite volume. It is that the volume is changing between liquid and solid, okay? And there was a lot of problem in the first experience that it was fully filled and exploded, okay? So it's never fully filled in order to allow to have difference of volume between liquid and solid. Very important. There was a lot of experiment put on the brick and so on. The brick were exploding due to the phase change difference of volume. So my remark regarding the important thing is to design, to identify the temperature of changing the phase, okay? Here, if I compare so energy which is stored with temperature, I take some water in red, okay? I start to bring it to this water tank, and it is linear, depending of the temperature. This is at 85 degrees, the energy that I have stored. If I have a phase change material, usually the heat mass of the phase change material is not as good as the water. Okay, is lower. Water is a very good materials with the density and the heat mass is very good. So you are starting lower, okay, but you are heating your solid, okay. Then at a certain point, you store more due to phase change, and then you continue. But imagine that you are operating here, okay, around 95 degrees. Finally, you store less energy with your phase change material than with your water, okay? Because we didn't identify the more appropriate phase change temperature for my application. So an important remark is that it's not because you are changing from sensible to phase change material that you will be more efficient. It has to be very caution on the choice of the temperature. And it is the main issue generally in the application. So people are speaking a lot of phase change material is beautiful and so on and so on. Not so, it's not an obligation. You can be less efficient. So it has to keep that in mind each time. If it was sensible heat, will it be more or less efficient? And for this, it's okay. If I'm operating here, I'm storing more energy than water, okay? But if I'm operating here, it's less efficient. So there was some attempt to put that on a very light wall in order to increase the inertia, the thermal mass of lighthouse, okay? Because existing buildings, in some part they are not inert and can store or can dump the heat effect out from outside. So there was some attempt to put some in some light wall, but it's very important to design the temperature. At which temperature we will put phase change material here? Is it 30 degrees in order to be able to absorb a part of it during hot time? Is it 25? Is it 35? There was two kind of materials that have been developed by chemical industry, Dupont-Nemours and BASF. BASF have developed some materials for construction like this, with two different temperatures. So it's interesting. There was a thing like this also to, as I told you, in brick. Okay, it was in such configuration. If you don't allow the kind of expansion, the brick will be fully destroyed. So I will, and another issue now is, so we speak a lot about heat storage, but the issue also will be to store the cool, okay, so at low temperature. So now there is also some study on at low temperature to be able to cool down materials that is able to phase change at also low temperature to keep the cool. Okay, so it's interesting also kind of materials to store when you are generating cool to keep this and to store it. Okay, so you can see the melting temperature that could be interesting to investigate. Okay, so at a bigger scale, so I speak about small scale phase change material storage for my domestic hot water. Bigger scale application is for concentration. We have seen that, but we didn't focus on the storage. Here it is a 2 tank that are for this Andasol, which is 50 megawatt, that allow to have an autonomy of 7 hours. Okay, typically it is during the night. Okay, because it is in the desert, so it's very rare that there is some clouds. Even if there are some clouds, it will not be during 7 hours. Is to have operating configuration night and day, so it's 7 hours. So we can have an idea. It could have to store 6,200 tons of phase change material, which is molten nitrate salt. Okay, so in this kind of tank, this is very corrosive, and this is very dangerous if there is a leak. Okay, that explains that it is classified, even if it looks like green power generation, it is classified as dangerous. Okay, so usually there is fireman not far. Okay, in order if there is a problem. It is Ménézo classification. Okay, to give you a rough idea of the size of such volume for phase change materials. Question? Okay, so we have seen that. For absorption, so there is several couple, lithium bromide, ammonia, O, so on. So the criteria is regeneration by heat, okay, and easy to handle, to couple, low investment cost, of course. Aging of the materials has to be taken in consideration. This is a classical way to store. Okay, we have already seen that for cooling system. It is the same. Okay, the same element. It's like a absorption machine. And so the coupling with the solar. So it's the same as the absorption machine, but it's not working continuously. When we separate the two media, we store them until we want again to have the heat. Okay, it's not a cycle where we are heating and cooling and so on. See, when we are heating during summertime, for example, we are generating a big, two big volumes of the two media, and during winter time, when we want this heat back, we put them together again. Okay. There is no, so it's summer operating condition, okay, and it is winter operating condition when you want to have your heat back. There is no real application for building at this scale long term. There was some prototyping. In my institute at Ines, there is one full-scale prototyping for a domestic house. Okay, try to have fully autonomy in heat for the whole year. Okay, so to give you an idea, I have not the picture, but to give you an idea, you have a house and you have a garage for your car. So the volume which is necessary to be fully autonomous in terms of heating needs, it is to fill the garage with the thermochemical materials. Okay, so it stay a big volume, even if it is thermochemical, it stay a big volume of storage. Okay. So you have the house and the garage, and you forget your garage, and you put the thermochemical storage here. To have, but you are fully autonomous. Okay. Of course, they have to have some improvement, and for sure it will gain in terms of volume reduction and things like this. Okay, so this is like a adsorption or absorption machine, but it is intermittent. You are operating in one direction during one period, and you are operating in the other direction during the other period. It's not a cycling like a machine for cooling. Okay? So what is important? It is operating temperature, energy density, but it is the case for all means of storage. For battery, it's also the case. The energy density of the battery, we have seen in our PV project that there was different battery with different energy density. That was in kilowatt hour per kilogram of battery. It's the same here. It's what kilogram hour I can store per cubic meter. Optimization of time of management, of course, it's a huge issue, and integration of storage in the building. That means that a lot of things are possible, but not in the building, because you are living in the building, and it is necessary to have safe system. Okay, safe system. If there is a leak, it has not to be dangerous for you. And if there is a fire, it has also not to be to enhance the fire effect. Okay, so it is it's a big limitation for building application, because there is many different couples that are very efficient in terms of absorption, but never seen in building because of these two parameters: sanitary reason and safety reason when there is fire. Okay. So the advantage, there is a lot also, not only some constraints, but you can really highlight the use of solar thermal thanks to this system. Image about storing of cool. Here it's micro capsule of phase change material. We call that ice coolie. Okay, so that you can also transport the cool on distance. So it is investigate not only to be able to transport it in the urban grid, but also to transport it, to transport cool, because the cooling needs are more and more big. Some example, you can put that also on the slabs, on the floor, on the structure. So this is for cooling. Okay, I've already said that. A short thing, I don't know what time is it. A short thing regarding grid. Storage is essential. So in the coupling with the grid, in order to optimize the flexibility. Storage could be for thermal energy, could be for electrical energy. Electrical energy, we try to couple the storage with electrical vehicle, to use electrical vehicle to store the electrical energy. But it is, yes, a key element in the management of energy at the scale of territory. As I remind you, you are producing, but you have also to transform, to distribute and to store in order to be well adapted to the energy need. Because you are producing very often when you don't need and you need when you can't produce. Okay, so even if you are connected to the grid, now more and more often the storage is becoming even for electricity. Okay, because of the price of electricity, which can fluctuate a lot. So it could be interesting to look at the storage of electricity on your car or in battery, to use it when the price is low, and to use this capacity that you have stored when the price of the grid is high. It's the same for thermal. Okay. You can mix with different energy vectors. It could be heat, it could be electricity, it could be hydrogen, and now in my lab some are playing with all these kind of vector to transfer to one vector to another, depending on the energy management and flexibility that you need. Don't forget that each transformation is inducing a loss also, so it's good to play, but you can lose a lot. So this is an illustration. There is many ways to store, to convert energy in mechanical, in thermal, low temperature, thermal, high temperature, in chemical, okay, in biological, and so on and so on. So there are many things in order to answer to the final use, even if you are coupled to the grid. This is in English, sorry. Yes, it's better. So for this you have to know about the grid, okay? And to enhance the power and quality and reliability, you have to trust in some sensors, some data, some huge need of control, because to control this complexity, to be able to anticipate. So that's the main issue that you have to take in consideration. This is the whole complexity of a grid that you have to deal with. I will not spend too much time on this, but more and more you need to have some data about the needs, about the condition of your system, about the condition of the grid, about the climate also, because the climate will change, could make the needs evolve. And so in our part, we are more working in the evaluation of the needs and the potential of solar at the scale of a territory, while considering the climate change, so kind of prediction of the meteo. Okay. Maybe I have not much time, but I will leave you read that. I wanted just to show you so that we are doing at the scale of city. We are working in two things: to be able to predict the solar potential at the scale of the territory, and to predict also the building need at the scale of the territory, due to prediction of both, so radiation, of course, but also meteo, urban climate. Okay. So we are using different tools like Solène microclimat in order to evaluate local climate, Rhino grasshopper, different tools. At that time, we are using some tools that are coupled to meteorological tools. Okay, so big scale, like weather research forecast. I will show you some results. And we are modelizing, taking in consideration the difference of energy budget that we have at the scale of a city compared to countryside. If we look at the energy budget of the city compared to countryside, this is what I receive from the sun. Okay, it is the same for urban and countryside. In terms, we see that there is a certain part which is reflected because there is lakes, there is trees. Okay, this part is much more smaller at the same as the city because the city is more absorbing. Okay. In terms of incoming infrared is the same. Okay. Then outgoing infrared, so it is what is emitted in infrared is 8.5 here, it is 10.3 here. That means that it emits more at the city scale than in countryside. Why?
You have a lot of carbon dioxide, greenhouse gases.
No, it is emission. No.
Lot of reflections.
No reflection. Yes, reflection is here. There's more reflection on the countryside than here. But here it is emission infrared. It is infrared emission is directly linked to the temperature of the surface. Emission of body is sigma temperature power 4. So here outgoing infrared is bigger because the surface temperature is bigger. Okay, so it's a good point, but it's not a good point because in reality, yes, temperature is bigger. Latent heat here is is a double here. So it is related to what? It is related to the activity of the forest. The trees are evaporate, okay, evapotranspiration, and also because there's water, lake, and so there evaporation. Latent heat is so the double here, whereas here there is less tree and no lake, except in the campus here. But very often there is no lake in the city. So you are evacuate more here by latent heat than here. Regarding storage, is 0.3 here, it's 1.3 here, because majority of the materials in the city are storing energy. It's sensible heat, concrete, road, it's heavy materials, it's good, sensible heat storage materials. So we are storing more. And sensible heat, what is related? See, it's a bit more in cities than here. What could be this sensible heat extraction? It's related to the wind. When there is wind, if you look at this far away, it looks like an heat exchanger. So when the wind is crossing, there is kind of induced phenomenon. So you have more convective heat exchange. So sensible heat is a bit higher here than here. And you have this green arrow, which is an injection of heat. And it is anthropogenic heat. It is related to human activity. Classical cooling system. Okay, these are rejection outside heat. You are taking inside heat, but you are rejecting outside heat. So if we generalize that, it will induce the rejection of heat here. You have also car, circulation, traffic jam, industry, and so on that are releasing heat. Car, an engine efficiency is 30%. 30% is used in mechanical to move. 70% is rejected as heat. So this is a key issue also, that you are bad balance in terms of energy, thermal energy, due to absorbing. Most of the surface are absorbing. They are dark. The roads are dark. The roof are dark. And you are absorbing. You are storing because it's heavy materials. And you are injecting more heat due to activity. So cooling system, traffic jam, and so on and so on. So this made it's necessary to modelize that in order to have an idea of the temperature in the city, in order to have an idea of the needs in terms of energy. It will impact the energy needs of building, okay? And to find solution to try to cool down, to mitigate this without injecting heat. So the main issue is that we will develop more and more the classical cooling systems that are efficient, but that are rejecting it. The more we will need to cool, the more we will induce a necessity to cool. It's very important to be aware of that. So it is in this way that solar thermal cooling systems are interesting now, because they are not rejecting heat like this. And centralized production of cool also, it's also an issue. Okay, I can speak for a long time about that. It's about urban planning, but I want to show you the last results I have with a PhD working in modeling of local climate on the base of the modeling of big scale meteorological. So he's using the tools weather research forecasting model, WRF, and try to model at the scale of a territory and then go down at the scale of a city to evaluate this. This, for example, for the city of Lyon. So here it's a part of France, Switzerland is here, my institute is here, and Lyon is here. So he's working, you see the scale on which he's working, multi-scale, so it is the quarter southwest of France, and then going down to investigate at the scale. So it's very computation consuming. And there is identification regarding the different districts of Lyon, possible different local thermal zone, okay, due to morphology, due to the size of building, the color of the building, the composition. So there are 10 different climates have been identified due to the morphology of the city. And so now is kind of clustering of this, all of these 10 climate can be seen. So it's analyzing the shape, the morphology of the district. And then to give some data like this, where you can have the temperature, the radiation, depending of the different districts. But it's not so nice at this scale because you don't see really things, but it's to classify the different zones of the city in order of local climate, and then after to be able to make the link. We are interested to see the climate and to see if we put some PV panels in this climate, what it will change in terms of local climate. Will it be worse or will be better? There is still a controversy about that. So he's testing different surface emissivity and surface composition to look at the impact on this. And so at the end, he is able to, in a different place, to give the temperature, local temperature, depending of the morphology he has chosen and the building envelope characteristic, and especially PV. Okay. So, I can maybe conclude on it, but I will leave you all the information if you are interested by the other topic, which is able to identify the real building needs, taking in consideration a more realistic climate, and then to make the link with the way to answer to the building needs thanks to solar energy. Okay, thank you. So this afternoon we will have the tutorials about desiccant cooling. Okay, so take the paper sheet with the diagram, the principle of the desiccant cooling components that has been sent, I think, to the people online, and we will see more deeply, but roughly the main principle of this system and the main consumption in terms of electricity and water compared to a classical one. Okay? And if we have time, design the thermal storage in order to be able to maintain stability for 3 hours if there is no sun. Okay? Thank you and see you soon.
So it's a very nice presentation. We have learned many things today. So like cooling and heating by using solar, and also at different temperatures how we can use it. So it's really very interesting. So no, and the very interesting thing what we received an email. This new scheme with India and France has opened for internship and all. It's a very good news. Just now I received an email. Thank you. But what I request you everyone, please be here before time. 3 o'clock we are going to start, but please be here by 2:55 or 50. Okay. Thank you.
Thank you.
And also there is an announcement today evening. We have arranged one dinner in our department, and maybe before we start for dinner, there will be one movie screening. Okay, that's we are planning what movie we are going to screen, and not exactly movie, it's a documentary kind. Okay, then we will have dinner. Right. Okay. So thank you. See you at 2:50 here.
কিমান আছে তিনডাল আছে ন তিনডাল আছে ন স্যার আছেতো
এইডাল আছে
बेलगावी परोसने का स्टाइल अच्छा लगा मुझे।
हाँ
हाँ बहुत अच्छा लगा कि मतलब और सब लोग इन्वॉल्व होते हैं ऐसा, मतलब मैं वही सोच रहा हूँ। पहले दिन जब आया था मैंने फोटो खींचा था, ऐसे सब नीचे बैठ के
हाँ
20-25 लोग काम कर रहे हैं।
वो वेजिटेबल कट करने वाला
हाँ,
था। हाँ उसमें पूरा
वो
कोकोनट
मतलब वो दिखता है ना कि तो ईगो वगैरह कुछ नहीं है, सब लोग
हाँ
काम कर रहे हैं ऐसा।
हाँ
नहीं तो हमारे यहाँ प्रोग्राम मतलब अरे बुआ ऐसे होगी, चाचा ऐसा होगा।
वो भी मतलब ऐसे पार्ट ऑफ कस्टम ही है,
अच्छा, अच्छा।
वो एक प्रोग्राम ही है, मतलब वो वेजिटेबल कट करने वाला।
तो पहले दिन में कुछ समझ नहीं आया खाना का,
हाँ
सेकंड दिन में समझ आया। अच्छा।
Hello, hello. Oh, dili na ka ba? Eh? Novenda. Oh, di sini. Pasnya na ba? Ada udah. Jadi hi takut ya, lo boleh cukup apa aja nanti. Apa dia lo?
They will do that. No, this is me. Okay. They will take.
Can you hear me? It's okay? I don't see. Can you hear me? Okay. Okay, so this tutorial is dedicated to study desiccant cooling, and as I told you this morning, to see the main difference to your conventional cooling system. Okay, of course, this system and the conventional cooling system should do the same thing. We want to have comfort, so the principle is to have outdoor air, to treat this air in order to have inside comfortable condition. Whatever the system, it has to have the same final target. So just to remind you the process, here you have external air, which is hot. Here you have the exhaust of air, which is cooler, okay? So then first you will deshumidify, okay? Desiccant cooling is to dehumidification. Okay, so this dehumidification, we will see the kind of transformation. Then you are going through a heat exchanger. Here you have cool air because it's inside and you are cooling, it's cool air. You cool down again here. Due to evaporative cooling. This is evaporative cooling. Cooling. You cool down in order to have a lower temperature before the heat exchanger. Okay, so the hot air will give heat to the cool air and we cool down. Then is crossing evaporative cooling, so the temperature will be lower and then it is blown inside the house. It's just an image. We don't blow at the bottom and we don't aspire at the top. It's just an image to see what is injected in house, what is extracted from this house. Okay, so the cool air is then extracted, cool down, heat exchanger. Here you are injecting heat through also a heat exchanger in order to increase the temperature and then here to extract the humidity. Okay, so solar thermal energy is there to heat this air in order to be sure to extract all the heat. Okay? Solar thermal collector. It could be a flat plate. Covered. You don't need to be over 130. And it is coupled to a thermal storage. When there is no sun, in order to still continue to provide heat to this heat exchanger. Okay. So now about the transformation between 1 and 2. It is a adiabatic deshumidification. So no exchange of energy, but T2 is higher than T1. It is a paradox, but we start to hit, we start to increase the temperature because it's a adiabatic deshumidification, and adiabatic deshumidification, we will see on the diagram, will induce an increase of the temperature. It's not good because we want to cool, but we start to increase the temperature. Between 2 and 3, it is a simple cooling. Simple cooling, that means that there is no deshumidification. When you are cooling with active cooling system, you can have condensation at the heat exchanger and loss some humidity. Here it's just heat exchanger, yes, simple heat exchanger. So you have no deshumidification. Humidity still remains the same, but you are decreasing the temperature. Simple cooling, so humidity is constant, and T3 is lower than T2 because the air has provided some heat to the cool air through the heat exchanger. Okay? We have a heat exchanger, the air is hotter than the extracted air, which is cooler. So the air is providing some heat and cool down. So the temperature, finally, as expected, first the temperature is going down. Okay. Then from T3, so from 3 to 4, it's adiabatic cooling, humidification. So it is the evaporative cooling, what we say, evaporative no exchange of heat, but T4 is lower than T3. Okay. It's okay for all transformation? Yes, exhaust air. And external air inlet. Yes. Outdoor air which is going in, and here rejected air. It's okay for everybody? You agree with that? Hmm? It is thermal storage. It is a solar tank. Solar tank. That allow to provide it when there is no more sun. Okay? It will allow when there is no sun, the thermal storage will provide the energy to the heat exchanger. So you tell me when it's okay, I will erase a part of So 1, 2, 2, it is dehumidification, adiabatic. It is a reverse transformation than between 3 and 4. Okay, you are dehumidifying chemically, and you are evaporative cooling. It's a reverse transformation, so it's adiabatic, and the temperature is increasing. Then a simple heat exchange, so simple cooling, okay, same humidity, but the temperature is decreasing. Then evaporative cooling, okay, so evaporative cooling, it's an adiabatic transformation, the temperature is decreasing, okay. It's okay, I want to erase this part. Okay, now I will follow the air that I want to reject. So, between 5 and 6, now you are able to tell me what is the kind of transformation. It is evaporative cooling. Okay, so it's like between 3 and 4. It is evaporative cooling. So it is adiabatic. Adiabatic. No exchange of heat, but T6 is below T5. The objective is to increase the temperature gradient before going in the heat exchanger. If you increase the difference of temperature between this air and this air, you enhance heat transfer. Okay. Then between 6 and 7. So it's heat transfer, simple heat exchanger, okay. So we know that 6 will warm after to become 7, okay. So humidity stay stable, same humidity. So it's a simple heating. Humidity is constant and T7 is higher than T6. Then between 7 and 8 it is the same. Okay, we just upgrade the level of temperature, but we inject heat, so it's also simple heating. Between 7 and 8, the same. Simple heating, and we know that T8 has to be higher than T7. Will be, for sure, we hope, if we have, it is all our solar system, T8 to be higher than T7 and the same amount of humidity. Finally, this air go through the desiccant wheel, and the target, the objective, the main aim is to extract all the humidity. So that means that this air will be humidified, okay? And it's also the same, it's a kind of evaporative cooling, okay? This air that will be through this desiccant wheel will take the humidity and it will have evaporative cooling, okay? So between 8 and 9 it is also evaporative cooling. We don't want to cool, but we want to take all the vapor. Okay. So it is adiabatic, and we know that T9 will be lower than T8. The objective is not to cool, is to extract the humidity. Is it clear? So this is the main principle of operating, and we know that. So we make some assumption to be more simple. So I put the assumption on the file as sent to you, but it's also here. We will say that the mass flow rate of dry air here will be the same as the mass flow rate of dry air here. Okay? Assumption. Mass flow rate of dry air inlet is equal to mass flow rate of dry air outlet. So just to simplify the thing is not more complicated to consider that it is different. But the other assumption that I'm doing in order to be more simple, but it's not so much complicated to, is that the heat exchanger is perfect. Okay, so that means that the heat which is provided here is fully taken here. Okay. No, it could be 80%. It will just induce more terms in the equation, but no more difficulty to consider real efficiency of heat exchanger. Okay, so I consider that heat exchanger are perfect. That each time I provide a quantity of heat, I'm sure the air is taking it, okay? And also, just to simplify and to not introduce some coefficient, 0.8 something. Or the aim is just to understand how we deal with that. And I give you as data that we are measuring the volumic flow rate, the global volumic flow rate at 0.1. The flow rate is measured at 0.1. It's very important when it is volume. Okay, volume is depending of the temperature, so it's important to see where we are measuring the volumic flow rate. Okay. So here we will come back here. So it's all the transformation that you can read. So my assumption are that heat exchanger has 100% of exchange. The dry air mass flow rate is the same at the extraction to inlet. And and also the other hypothesis is that all the humidity that is captured here is extracted here. Okay, but this is not an assumption. It should be the reality. If it is not the reality, there's a problem with my system. So the fact that all the humidity which is captured here by the desiccant wheel has to be extracted here, it's compulsory. If it is not the case, that means that the humidity here that is extracted is below this one, and at a certain stage it will be fully saturated and stopped. Okay, so it's compulsory that the humidity which is captured here is fully extracted here. So this is my three things. Okay. We know some point. We will come back later on this. We know some point of measurements, but not all the point of measurements. But thanks to the transformation, you should be able to discover all the data. One question: do you know this kind of diagram? Ah, okay. So I'm happy. So it's a psychrometric diagram. Just to remind you, this is temperature. Here it is the temperature. Okay. So this is small temperature, high temperature. What is this data? It is the content of humidity. So it is, so I call it air, but maybe you call it W, I don't know. It is, yes, specific humidity. It is the mass of water divided by the mass of dry air. All the data that are in this diagram are for 1 kilogram of dry air. It could be the same if it is a ratio between flow rate, okay? Of course. So when I said that for mass transformation, it is a simple heating or simple cooling, that means that this remain constant, okay? So now if I want, so this is enthalpy. So when I said it is adiabatic, as I'm open loop, I'm at atmospheric pressure, the difference of enthalpy is equal to difference of heat exchange, d delta H. Because I'm a constant pressure, okay? So when I say it is adiabatic, that means that H is constant, okay? So this is an adiabatic transformation. What else? For the first point to compute, we are not interested in the volumic flow rate. We are interested in the dry air mass flow rate, okay? So here you have the specific volume. Here. It is the ratio of the volume of the mix divided by the mass of dry air. So it's a ratio between mass, volume and mass, or flow rate, volumic flow rate. Okay? So that means if I give you the measurement of the mass flow rate okay, in point 1, you have to look at specific volume in point 1. From that, you can say that the dry air mass flow rate is equal to Q divided by specific volume. Okay, important to straight away to compute that. Like this, we just deal with dry air. So we want to cool down this seminar room in Guwahati, and so I estimate at 330 cubic meter, and we are measuring outside volume, so the volumic rate that are coming from outside. So we also estimate that the buffer tank, solar tank, is 2 cubic meter, but we will see how we can compute this, evaluate this capacity. Okay. So we have some data. For example, you are able to put to place the point 1, okay, on the diagram. 0,012 divided the T1. Ah, sorry, what have you done? What is the temperature outside? 30. So 30, okay, and you have to be at 0,012, so the point 1 is here. Then you know that between 1 and 2, what happens? Adiabatic deshumidification. So you know that you are somewhere here for the point 2. Okay. And you know the humidity of point 2, 0.06. So you know that you are here. So to plot the point 2, point 2 is here. Okay? Then you know that between 2 and 3 it is simple cooling. Okay? So you know that air free is equal air free. Bref, humidity is constant. That 3 is somewhere here. Okay? Can you give me the specific volume for point 1? And so we will deduce straight away the mass flow rate of air. Can you give me this value? I estimate that it is 0.875. Hmm? So now you are able to give me the air mass flow rate. Please give it me in kilogram per second. Kilogram of dry air. A kilogram of dry air per second. I have no value in mind, so I trust you. We can also make a statistic between all the data and choose the more.
Now, what do we like mass flow rate?
Yes. So, and I want it in a kilogram of dry air per second. Hmm?
kg per hour.
Yes, this is given by per hour. But for all the formula after, I need a kilogram per second because energy
Kilogram per hour?
per second I need. much? So point 857. Okay. So keep it in mind, it is a value that we will use everywhere because on the diagram everything is given for 1 kilogram of dry hair. Okay. Okay, what else we can plot point 4? Because we just know that R3 is equal to R2. Maybe point 4 will help us. Okay, so 0.009 and 19. So I'm here and 19. So point 4 is here, if I don't make a mistake. Four. Here. Okay. So, is it possible to plot point 3? Hmm? The answer is yes. For each point, you just need 2 information. And for point 3, you have 2 information. So first is that humidity is equal to the same as 2, and the second, so humidity is the same as 2. And second is that between 3 and 4 it is adiabatic, so it is the same enthalpy. Okay? Between 3 and 4 it is evaporative cooling. Evaporative cooling is the decrease of temperature and the same enthalpy because it is adiabatic. So we know that it's the same. So we have point 3. Okay. Same enthalpy because it's an adiabatic between 3 and 4 and same humidity as 2. If I forget that and I want to do the same thing with a classical heat pump cooling system, is it possible? What will a classical cooling system do? I tell at the introduction that my system has to do the same as a classical cooling system. Otherwise, it's not good. Okay? A classical cooling system will start from point 1 and will finish in point 4. A classical cooling system, as you have studied, I guess, the transformation of a classical cooling system is that you are very often deshumidifying and cooling. It is a classical cooling system, straight away. the air in outdoor air is coming, crossing, arriving at the evaporator of the cooling system, give some heat. A part of humidity is condensed on the evaporator, so lost, and is going out. Simple transformation. It is not a simple cooling. It is cooling plus dehumidification. Very often it is that. So a classical heat pump will do that directly. Okay, take the air, go to the heat exchanger, which is evaporator of the heat pump, lose a bit of humidity due to the condensation on the heat exchanger, and go out. So this is equivalent to classical cooling system, but with several transformations. This will allow us to compare to a classical one, okay? Because here, you know that the cooling, we are able to know the cooling power. Can you give to me the cooling power? Ah, sorry, it's not F. Cooling power is equal to the mass of dry air multiply delta H. The difference of enthalpy. So it will be P cool is equal to M dry air H4 minus H1. When you are studying a classical heat pump for cooling, it is this transformation that you have, and to evaluate the cooling power, it is evaluated like this. Okay? You are starting from one point, you are treating this to another point, and the power of cooling is mass flow rate multiplied by the difference of enthalpy. Okay? Can you give me, so this cooling power, that is the same for a classical one to this desiccant cooling. Okay? It's the same objective, of course. I want to reach the same target, to start at point 1 and to be comfortable when I blow the air at point 4. So somebody can give me this value. So you have to multiply the dry air mass flow rate by the difference of enthalpy that you can read here. The unit is kilojoule per kilogram of dry air. So, for example, for H4, it's around 42. The power? Minus 11, as I remember, it's a bit small. I was in head a bit more, but is there somebody that find 17? Yes, it's more. I had in mind around 16, 17. So can you give the H4 and H1 for everybody like this? 42? And 52? 62. Ah, 62. So 42.5 and 62.5. Okay. And so you have around 17? 17.14. And it is negative by convention. It's a cooling power, so you can. And the mass flow rate, you have to multiply by 0.85. You have multiplied by. Okay. So it is also the cooling power that we will require for classical cooling system, heat pump. What is the efficiency of classical heat pump for cooling? Yes, what is the kind of value we can expect? Maybe also 3. We can expect 2 or 3. 2 is quite low. So we will consider a good cup that could be 3. So it's very efficient. In order not to blame that system, to choose a very efficient one to see if we are comparable or not. So that means that the electrical power of your heat pump will be 17.4 divided by 3. Okay? When we give efficiency of a cooling heat pump, it is 300%, very good. And so the compressor, the electrical power is divided by 3. So a little bit less than 6 kilowatt, okay? 5 something. So the heat pump will have a power of 5 past 7 electric, okay? Now we will try to plot, yes, it's interesting at that stage. Well, we can continue on this. I want to see what is my power, electrical power of my system. Where I'm consuming electricity. You have the fan here and here. But even for classical HVAC system, you will have this double flux because you want to recover part of cool here. So the fan will be the same in the two configuration. Okay? But we can include them if we want. There is electricity here in the drawing wheel. Usually it is running very slowly. It is running very slowly in order to be sure to extract everything. So it's not a big electrical engine. we can say that it is around, if we 100 watt. Okay, here for the electrical, and here if we consider a rotative heat exchanger, so it will be 200 watt for electric engine of heat exchanger plus the wheel. Okay, if we want to be large, we can take in consideration the fan. So we can add 100 watt here and 100 watt here. But I tell that in principle it is the same also with a classical heat pump, but because we will have to manage the air inlet and the air outlet. Could have here a small pump in order to make it coming and so on. So this is very small circulator. It could be around 50 to 60 watt because it's like in a water system. So we can see that the maximum we are around 400 for 500 watt. Okay. So you see the difference. We have 500 watt, whereas for classical we were 10 times more. Okay. We were at 5,000 watt. So in a point of view electricity, it's good. We reduce this power by 10. So it's hopefully it is good. Yeah, because otherwise there is too much things that we should choose a classical one. Okay, so what we could be interested in as data. Maybe we will plot the other point, okay, like this we will see, but in principle we can be interesting by the water consumption. What is the water that we are consuming here? What is the amount of water that we are consuming here? Okay. So is it easy to express? Yes. Because we know R4, we know R3 multiply by the mass flow rate of dry air will give me the mass flow rate of water, because air is equal to the mass flow rate of water divided by the mass flow rate of dry air. Okay. So it is the mass flow rate of water that I'm injecting here only between 3 and 4, and we will see, we will add what we are injecting between 5 and 6. It's okay? I have before, after, so the difference is the humidity ratio, and multiply by the mass of dry air is giving me the mass flow rate of water that I'm injecting. Somebody can give me this amount? Mhm. So R3 is 0.006 and R4 is 0.009. Okay, so the difference is 0.003 multiplied by 0.875. Okay, so what is the value? 0.025. So it is kilogram of water per second. So if I imagine that we cool this amphitheater during our lecture, so 6 hours per day, okay, it gives you an idea of the water consumption just for the humidificator between 3 and 4, okay. So we said 6 hours of operation. So 0.0025 multiply by 6 multiply 3,600. So it is a quantity which is consumed between 3 and 4. Fifty-four kilograms, so 54 liters of water. Okay. We will see, it should be not far from 5 to 6, but we will compute that. So for this, it will be 100 liters of water. So if you are in a country where you need a lot of water, but you are consuming much less electricity, so it has to be a compromise. Okay, so 54 liters of water, just between 3 and 4, and we will see between 5 and 6. We try to plot 5, 6, 7, 8, 9. Okay. So I know 5, 23, and 0, 0, 10. 5, 23. So 5 is here. It's by chance that it is. I will erase that. Okay. What else I know? It is 0.6. 0.6, okay. I know humidification. So I know, regarding 0.6, I know that the enthalpy of 0.6 is the same that the enthalpy of 0.5, okay? And I know the humidity. So 0.6 is here, and I know that it is the same. So it's somewhere here, enthalpy. Okay. Okay, same enthalpy, and we know the humidification. Okay, it's okay. What else? No more information. I know that between 6 and 7, it is a sample heating. So I'm going in the other direction with the same humidity. Okay? I know that 7 is somewhere here because I'm heating 7. Okay? So R7 is equal to R6. And that I'm heating, so I'm going in this direction. What can help me to go to find 7?
Oh, sabi to lo issue naman. Totally in port now. Tomorrow.
It is the assumption that my heat exchanger efficiency is 100%. So that means that heat exchange, the quantity, mass flow rate of dry air multiply Cp T2 minus T3 is equal to mass flow rate of dry air Cp T7 minus T6. No. It is including two assumptions. First, that this is equal. Okay? The mass flow rate of dry air, which is coming from inlet, is equal to the mass flow rate of dry air, which is extracted. Okay? So this, and the other assumption is that my heat exchanger is perfect, so the quantity of heat which is given by 2 and 3, between 2 and 3, is given between 7 and 6, okay? So finally, I know that T2 minus T3 is equal to T7 minus T6. Okay, I know that this is equal to T7 minus T6. So now you can determine exactly T7 because you know 6. We plotted T6, we have only this value, but we know that between 5 and 6 it is adiabatic. So we know that H6 is equal to H5. So 5 is here. I know that between 6 and 5 it's adiabatic. And I know that the humidity of 6 is here. So 6 is the intersection of this adiabatic and with this line. To T6, I estimate T6 to be a bit more than 18. 18? 18. So you can deduce T7. If I want to go fast, I measure this and I plot it here and I estimate 7 here. Okay? Because this is T3 minus T2 and this is T7 minus T6. Okay, the length of, yes. But if you want to be accurate, you compute T7. I approximately estimate T7, you can tell me, to 36. But very fastly. But if somebody wants to compute T6 to T7, it will be better to have the right value. 36? So I'm good. 36. Okay. So we have the air is looking like this, then is in 6, then is going like this till 7. Okay. So what? Then after 7, there's again heating. Okay. to go to 8. So 8 is something somewhere like this, on this. We know that it is a simple heating, so 8 is somewhere here. But we don't know other indication about 8. We know 52? Ah, okay. Okay. But in principle, we can exactly compute it. How? How we can exactly, even if I didn't give you the value of T8. Yes, MCPDT, but you don't know the power that is provided by the solar collector. It will be to be computed also, to know after what solar collector you put. Okay, at the time we don't know what is the power that has to be given by the solar collector, so no information yet. What else we can use and we didn't still use? There is one thing what we don't use again, and it's compulsory for this system. It's very strong constraint. What is it? Yes, is that the amount of humidity that is collected here has to be extracted here. So that means that the amount of humidity which is collected here what is collected between 1 and 2? It is mass flow rate of dry air multiplied by R1 minus R2. This is the humidity which is catched by my wheel. Okay? And it has also to be fully extracted here. So fully extracted here is that means that it is equal to dry air mass flow rate of dry air multiply R9 minus R8. Okay? This is compulsory. Okay. You have to extract this amount of humidity, which is exactly the same of the amount of humidity that has been collected by the wheel. So, same, you know that this is equal to this. So, you can also measure that the length you know that this length, okay, R1 minus R2 is equal, you know that R8 is here, okay? We said that humidity of 8 is here. So has to be equal here. So here you have R9. Okay? And you know that you have also isenthalp between R8 or R9. So you can be like this. You can be here, here. Okay. So you can plot R9. Okay, we have all. So R9 is not comfortable. Huh? You are around 38 degrees with high level of humidity. Okay, a lot of hot and humid air which is rejected. So now we are able to identify the other part of you are able to identify the other part of humidity which is consumed, of water which is consumed. It's here. It is mass flow rate here. It is mass flow rate of dry air. It is the consumption of water for the top. Compared to between 3 and 4, it will be a bit less. Okay, 3 and 4 we identified it was 54 liters between 3 and 4. Here you will see that it is a bit less. We can estimate globally the global consumption. It will be probably 80 liters. Okay, just to have a rough idea. But you can compute exactly the quantity of water here that you have to add to 54 liters. So it will be around 80 liters globally consumed in terms of water here, because that was missing in terms of water consumption. Okay, but you can exactly compute the quantity of water which is consumed. So global, it will be around, I estimate between around 80 liters of water it consumed for a whole day of operating. Okay, it's clear for everybody. So now we know how it's operating, we know the power of electricity, we know the quantity of water that we approximately consume. We now have to design the solar collector. Okay? So one of the key elements is what is the power that we have to inject here. Okay. So the power that we have to inject here is equal, if the heat exchanger is 100% efficient, all is given, it is a mass flow rate of dry air multiplied by H8 minus H7. So the total mass of water is this. Sorry, I will finish that. Is plus R6 minus R5 multiply mass. This is the total of water consumption. Okay, now if I'm focusing on the power that has to be bring by my solar collectors, it has to be bring here between 8 and 7. So it is the mass flow rate of right here multiplied by the difference of enthalpy. Okay. So I will appreciate if somebody can give me this power. Sorry? 11.2. 11.2? Can somebody check and confirm? So my solar thermal system has to bring this power. So depending of the area, the mean irradiation, efficiency of solar thermal, you can. Yes, so you can have estimation of the surface of the solar collector. Okay? So then, area or surface. So you have to investigate the mean solar radiation, the efficiency of the solar collector, and to evaluate the surface. So as Pankaj has introduced you in the first lecture. Okay. So there is no special difficulty to size this. What I want to focus is about the tank. Okay. To finish. So the tank has to be designed in order to bring an autonomy. All the time the same. It's the equivalent of a battery for solar PV. Here the tank is to bring autonomy if there is no sun. Okay. As I said this morning, there is no sense to have an autonomy of 3 days for a cooling system for this amphitheater. It's at the scale of the day. Okay. So we can imagine that this morning we were producing solar thermal, and this afternoon it's becoming cloudy, but still hot inside, that we have to cool. So we have to bring energy, sufficient amount of energy, through the solar tank to be able to keep on cooling. So a good assumption will be to have around 3 hours of autonomy. This morning it was operating. This afternoon there is no sun, but during 3 hours we are using this amphitheater. Okay, so we said 3 hours. Three hours of autonomy. What is important to determine now? To be able to size my tank. Hmm?
3 hours.
Yes, 3 hours. So I assume that this morning it was fully operating because it was sunny, and this afternoon it's becoming cloudy, but it is still hot because it's a hot day. But I need to cool down because we are here and it is still hot. Okay, so I want that my tank provide me the equivalent of the energy that will have been provided by the solar collector. So it's important to know the autonomy. So I said 3 hours, okay. And the other, so what is important now to know? Hmm?
The hot water, what we generate from.
No, I assume that this morning it was fully sunny. The solar collector was generating heat for here. That it's what though I assume that when there is no sun, my tank is full of energy. Okay.
For 3 hours.
For 3 hours. So what I have to compute? The amount of energy that I have to store. Okay, so the amount of energy that I have to store is the power that I have to provide multiplied by the time. Okay, so energy, thermal energy is power of heat. So 11 2 okay. So can you compute this? So you can, if you don't multiply by this, you will have directly kilowatt hour. It will be 3. But we will have to have it in kilojoule for the sizing. So you have to multiply. You have to multiply that per 3600. Okay. So I have my amount of energy. But you know that for thermal is not enough, because we have seen for hybrid photovoltaic thermal collector that for thermal energy is 1 point, but the quality of energy is another point. Okay, so I can have a lot of energy, but if the temperature level is not enough for my process, there's nothing. Okay, so at least what temperature I have to have, and it will give me the assumption of my operating of my tank. Okay, so first I can say that if my tank is fully charged with a flat plate collector, I can estimate that the temperature here could be around 80 or 70 degrees Okay. Yes. Yes, stagnation temperature. Okay. It's fully charged, or I can say 70. Okay. So it is a starting point. But I have to consider a final point, because when I will start to extract some heat, okay, I will not go at 30 degrees. 30 degrees is not enough for me. What is the temperature that I have to reach at least at the smallest temperature? Hmm?
Just more than body temperature.
More than T8. Because if it's less than T8, I will never reach T8. Okay? As soon as here the temperature is lower than this point, for sure I will not able to reach T8. Okay, so T8 is around 52. Okay, we said 52 for T8. So we can make the assumption that this amount of energy has to be provided, okay, but the operating range will be 70, for example, or 80. To be sure, we can say 55, not 52, because they will have loss of the heat exchange and so on and so on. It's better to take a bit more than T8, okay? But for sure, this has to be higher than T8. Because if it is lower than T8, my system is collapsing. Because I will not be able to extract all my humidity. Okay? So at least I have to reach T8. So that means that under 55, my energy, I have still energy, but I don't care about this. Okay? So it's clear? So how I will size my tank? I will say that my tank has to provide the volume of my tank. Okay, it is the volume of my tank multiplied by the density, multiplied by Cp of water, (70° minus 55). Okay, this is the amount of energy that my water in the tank has to provide me. And it has to be equal to that. The amount of energy which is necessary for my desiccant cooling system to operate during 3 hours. Here I know everything except the volume. The data to compute is the volume of my tank. Okay? So we can finish on this. If somebody can give me the volume, like this, everybody will have an idea of the volume of the water. Maybe if somebody can give me the total energy that has to be provided in kilojoule. So 209.
Volume we can see 1.929 cubic meter. Almost 2 cubic meter is the volume.
Ah yes, but okay. So volume, how do you find?
1.929. It's almost 2 cubic meter.
And the total amount of energy in kilojoule. Like this, everybody will have this data.
There, 70 minus 55 should be greater than T8. Set here, near to auxiliary, near to auxiliary tank.
Yes?
70 minus 55.
Yes. It is a range of operating.
So you use range from there.
Yes, because when there is no sun, okay? So the heat will come from this tank. That means that the temperature in the tank will decrease. Okay? I will start at 70 when it's full of heat. And with an heat exchanger, I take the heat, okay? And so the temperature will go down, down, down. But I have to stop when I'm close T8. Because if here I'm making a fluid which is under T8, for sure I will not reach T8.
We have seen that T8 is 52.
Yes, T8 is 52, but it's dangerous to take exactly T8. Because here you have efficiency, you have loss, and so to take exactly T8 is a bit dangerous. It's better to be a bit higher. So I decide to say, instead of 52, I will stop at 55.
My question is, while calculating the volume, we said 70 minus 55.
Yes, it is my operating range. I said that here I will start at 70, the temperature will decrease, 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 and I stop at 55. To be sure that my system will still operate. Because if I'm at 52, I will not reach T8. The objective is to reach T8, okay? So if here I have a temperature equal to T8 or under T8, for sure I will not reach T8.
Actually, I think his queries is something like 55. It's 55, not 70 minus 55, right?
Yeah, that's right.
It is 70 minus 55.
Its difference is 15.
Yes, 15.
Actually, its temperature is 55. So this T8, at T8, this temperature has to be more than 55.
No, T8 we know that it has to be 52.
52, T is 52.
Yes,
So what I am saying, this 55 is more than 52.
yes, so it's secure.
Actually, no, what he is saying, he understood that 70 minus 55.
Yes?
It is 15.
Ah no,
Not actually minus.
it's minus here because it is the energy that your hot water is providing. Your tank is providing this amount of energy, starting from 70 and stopping at 55. So this is provided by the tank, okay?
That's a range, not difference.
Sir, in this formula, delta T is there or only single delta?
No, delta T is 15 here. In this formula, it's 15 here.
See, what I could figure it out. See here, T8 what we have investigated, it is 52. Okay, so what up to what temperature this water can drop? Up to 55. Up to 55. So that 55 temperature, that no, say T1 minus T2, T2 if we consider, or say TA minus TB, Okay, this TB is 55, and TB has to be always more than T8. Okay, and here what happens? This has to be this one. This energy, this thermal energy, has to be something like MCPDT only. Why MCP is something like rho into V. Okay, so the same thing. They are not disturbing. So in my opinion, what you have confused is 70 minus 55. No.
Ah, no,
It's
no.
it's a range.
It
It's
is-
a range.
It is
It's
this.
a range. It's not minus.
It is
It's
this that has
It's
to be.
55.
This
Yeah.
lower temperature has to be higher than T8.
Yeah.
It is the lowest temperature that has to be over T8. Sorry. Yes, it's there is everywhere. So it is this temperature that has to be higher than T8 to be sure that the process will operate. So in principle, I can take T8, but it's a bit dangerous, okay? Because for sure you will have heat loss and things like this. If here you have a fluid with T8, 52 degrees, the risk is to be at 50, 51 here and not at 52. So to be sure, I choose to be a bit over T8 at the minimum of the temperature coming from the water tank, okay? Is it clear? You fully understand the system? After we can play again, but we stop maybe here. But we can say, okay, instead of water in the tank, I want to put phase change materials. So what be the volume if I put inside here some nodule of paraffin, and I can give you the latent heat, the specific heat, and so on. So the energy that will be provided by a phase change material, of course, has to be the same. If I put phase change material, I have still to provide the same amount of energy, for sure. It will not change. It has to be equal to ρ1, C1, V, phase change material when it is solid. T1 minus T phase change. Okay, it behave like a sensible heat storage when it's still solid. Plus, when I reach phase change temperature, what happens? Latent heat. Latent heat multiply by rho V. Okay? The mass. Then it is fully liquid. If I continue to use this energy, it could be rho 1 or rho 2. Usually we take the same. C2, it depends. Volume, T phase change, minus T final. Okay? So this will be (55), the lower temperature. Then I reach the phase change material, and this will be 70. So it gives you also an idea of what kind of phase change material you have to choose. When I see that, it's good to find a phase change material between 15.5 and 70. Okay? So if I find a phase change material with a temperature of phase change around 63, something like this. Okay, it's good. 63, 64, 62. It's good. Okay? It gives you an idea of the phase change temperature. So there is many phase change materials, many. So, and I said that the key point is to have this temperature. So you know that you will operate between 55 and 70. So it's good to find in between. And so the equation is a bit more longer, but the thing to be computed is still the volume. Okay. Do you have any question? And so hopefully you should find that the volume is divided by 2 at the end. If you find that the volume is higher than water, it's not good in your computation. Okay? Just to give you an idea, when you go from sensible to phase change, you can almost divide it by 2. So, and if you are changing with thermochemical, you can again divide it by 2. So if it's impossible to find a higher volume than sensible, and you have an idea of what you have to find if you select a good phase change material. So you should be around just below 1, something like this. Okay?
What could be the TR value?
Hmm?
TR. TR values.
Where TR?
Last. Before T final.
TPC, it is T phase change. Phase change here. Sorry. It's phase change. There is 3 temperature. You start the final. It's 55. Is the phase change temperature, where you have that, and then you are starting to the phase change temperature to go to the highest temperature. So it is T phase change. Other question? So thank you for your attention. You are very concentrate, and
Very good problem.
okay. And so if you have other question, don't hesitate.
Maybe we can extend the problem again by using thermochemical.
Yes, we can continue with water and lithium bromide to see. Yes, you can continue.
That may be homework for us.
Okay, thank you, and see you soon, tomorrow or tonight. Bye-bye.
So thank you for your concentration and actively involved in solving this problem in the tutorial class. So we are meeting again today at 7 o'clock. Okay, because there will be one documentary telecast in the School of Energy Science and Engineering conference room. So please be there by 7 o'clock in the conference room of School of Energy Science and Engineering, and followed by dinner. Okay, so see you there, and please be here tomorrow at 9:20. Okay, we'll start sharp at 9:30 tomorrow, and then anyway tomorrow also it will be long, because tomorrow also it will be long, because at the end you have to go with your certificate. Okay, and so many things to do. So thank you. See you then at 7 o'clock.